will be back and
This meeting is being recorded.
just let me back to us. Okay, so we are 56. I think that we can start, otherwise we will accumulate late. And so Jota, I will give you already the floor directly. I mean, you don't need any sort of introduction for
Yes.
this section. And should I start with the presentation? So
Yes. Yes.
okay.
Thank you.
Please.
Yes, thank you, Angelica. So after the installation yesterday, let us see now in more detail what we are going to do during this Train the Trainer session. And you must have noticed already under the related tab in the Indigo agenda that there are several colleagues involved, and of course, thanks to all of them, particularly Niklas, that he's sacrificing part of his vacation. So in the next slide, let me start with the question, what does it mean train the trainer? Well, you have heard already several times during this course that you have been selected out of many applications, and this course aims at educating the next generation of experts, the leaders, for the next generation ion therapy and research facilities. And it is financed by you within the HITR Plus project, which includes in the education and training work package 3 courses. In order to facilitate sustainability and to spread the acquired knowledge and create a kind of a cascade effect, they all foresee train the trainer sessions. So we have to provide you with the means to become tutors yourselves. And this can easily be done within the masterclass framework that we have developed and which is based on the MATRA treatment planning toolkit that we installed yesterday. So in fact, you can find the useful material and recordings of the lectures and hands-on of the first school, the Heavy Ion Therapy Masterclass School, that was focusing mostly on the treatment planning. For sure, we cannot do so much in one afternoon, but you have the workflows uploaded in Indigo. And as I said, please check the Train the Trainer tab and Indigo links to the previous courses and recordings also. So in the next slide, so we'll focus today on learning how MATRAD works and practice preparing treatment plans. And then we will go back to the content of the master classes the last half hour, while we will close the session with a fun quiz that my colleague Albana Topi from GSI will present. So Niklas will guide you through the workflow, and hopefully you will have all installed MATRAD so that you can do it yourself. If you were not able, do not worry. You will follow the course and then you will do it at your own time with us helping you remotely to do the installation. Please remember to submit your exercises to the emails that are noted here by 11th of July. And then we hope that you will be able to do your own master classes back at your home institute, as we will discuss later. So Niklas, now the floor is on you. Angelica, you can stop sharing and then we'll share. Thank you, Niklas.
Yes. Hi, can you hear me? So
very well.
Yes.
Good. So my Wi-Fi is okay. I figured out. So but I could at some point skip out for a few seconds. So that's what I tested yesterday. So if you're not hearing me anymore, you just quickly let me know. Yeah, so we had a few, like I think 2 or in total issues with the installation of the software. So what I could, I can at the moment now not kind of fix these as Jota said. So, but you can basically write us an email, and if you have an issue, please tell us everything important, like what operating system are you on, what which version of it, and so on, so that we know what's going on. If we just have an error message, we do not know why this happens, because on our reference systems it works. But we had one issue with too less space, or no admin rights, so that's quite clear. There's kind of nothing you can do, and then you need to check maybe for a different computer or else. Regarding the exercises, so I have prepared, so the idea for this course was a little bit really not to run you through exercises one by one, but basically explain the software to you and what you can do with it. So can you then start your own research project with it, or can give or that you can give a course with it. So the idea was now that I will basically give a short introduction with slides just to tell you what the software is about. Then we will start up the software and check out all the important bits of it. Take a little look, make maybe one kind of or two treatment plans in a sense, so that we know what are the important functionalities in the graphical user interface, what can you do with the code, and how can you work with this like dualism in MATLAB between scripting and interface. And the last thing is then that I have one exercise basically, which I will give you enough time in the end to kind of do yourself interactively, so without me just telling you what to do, so that we also have kind of a little discussion, and you have the opportunity to ask a few questions in the end, and maybe some of you also manage to solve the installation issues until then. I have to check, is Noah actually in the, yeah, Noah is in the meeting, so you might consider writing Noah a direct message, because he might be able to Google an error message and discuss with you about the operating system and figure out what you could do to install Madrat if it didn't work. Okay, so I will start to share some slides. Maybe a little bit about the whole context of Madrat. It's all about treatment planning, which is a heavily computerized process. So you all know you need software for that. So when you're basically working, for example, at the clinic, you need a software before you irradiate the patient to numerically simulate and optimize the dose, which is then called treatment planning. And there you have a very heavily developed, well-tested, well-commissioned system, which is closed. It has some scripting interfaces, but these systems are usually closed. You don't have access to the algorithms that are in there. That's of course because of IP and also for safety reasons. So even when you have an in-house treatment planning system that was developed by research engineers or software developers inside the institution, it's usually very heavily guarded that you don't make modifications there that kind of interfere with some important functionality like a dose simulation. And in research, of course, that's not always what you want. So when you're doing treatment planning studies, that's exactly what you want. You want a system where you can just do treatment plans. But when you really want to create, let's say, new dose calculation algorithms, which is working more and more towards Monte Carlo software, or you want to try a new treatment planning strategy, like define a new dose optimization problem, and so on, you really need software where you can modify the stuff. You can modify the code, and that's where Madrat comes into play. So this should give you the opportunity to really modify code and also, of course, spare let's say, it's a little bit ironic, spare the cost for a treatment planning system. So MATLAB is in MATLAB, so there's still some cost if you want to use the user interface or you need a license for that. But there's reasons why you use MATLAB, and that's coming later. But of course, these costs are much more smaller than what you pay for a treatment planning system. They have huge licensing fees that you have to pay annually. So that's usually not feasible, for example, also in an educational setting. So what are examples for research topics at the core? For example, like if you want to, so an example of a recent paper that used MATLAB, not the paper itself, but for example, I saw some papers using MATLAB to create a new quantity for flash treatment planning depending on oxygen concentration. So then you have to modify the optimization, have to modify the dose calculations. So biological planning, for example, or something that we did is that we modified the dose calculation to be probabilistic and also optimize this. So this is all heavily intrusive stuff that such a treatment planning system can be helpful for. So we usually call MATLAB a toolkit for three-dimensional intensity modulated treatment planning. And the main modalities that are in there now in the release that you downloaded are photons, protons, and carbon ions. It's entirely written in MATLAB. So as I said, the best way to run MATLAB is to have MATLAB. But you can also run at least the code, not the graphical user interface with GNU Octave. And the license is a GPL v3, which is a copyleft license, meaning that, let's say, if you like want to use, or if the example, if for example, a company cannot just easily use it and build their treatment planning system around it and don't share back their developments. So when you build a software based on a GPL licensed software, you always need to license it open source at GPL as well if it is dependent. So this just kind of protects that the developments that come out of MATLAB kind of also go back to the community and are not then misused for products without the community not getting any of the developments back. Yeah, so MATLAB implements well-established radiotherapy algorithms for research and education. Of course, the algorithms that we have there are not extreme state-of-the-art in technique and performance. That's just because there is so much optimization and development effort there that you can barely beat a very good commercial treatment planning system, which has, I don't know, 100 developers just optimizing code and building new functionality. But you can all, you have code that was used and still sometimes is used in treatment planning systems all over the world. So you're not doing things that are wrong within MATLAB, but you're maybe not doing them as fast and as efficient as in a real treatment planning system. Yeah, so, but you have all the code, you have example patients from an open data set and generic radiotherapy machine files included in it. You have a graphical user interface that you can use and which will also be available in the standalone. The optimizer that we use can kind of accommodate a wide range of planning objectives. So you can build a lot of optimization problems since it's a nonlinear optimizer that also allows nonlinear constraints. And it's kind of, let's say, almost in convex optimization, that's the most global you can get, because nonlinear function kind of includes also right linear functions, and nonlinear constraints also include linear constraints. So in a sense, you are covered in this way. And you can also import DICOM files, or let's say most of the DICOM files. Sometimes we have issues, but we always try to get ahead of them because the DICOM standard it's a standard, but it's not, let's say, it's the least standard, so there's often a lot of variations in the files, and some tags are not set even if the standard requires them. So you might experience some issues, but there we always try to fix them really quickly so that the DICOM images are understood. And you can also export back to DICOM. You cannot export RT-plan though, because we do not want people to plan and feed these plans into their treatment planning systems. But you can also export some binary formats, so doses, CTs, and so on, you can export. Yeah, as I said, if you have no MATLAB, you can have the standalone, which some of you installed, or try some stuff with Octave, but there the user interface is not supported at the moment. Yeah, and our goal with this is to support open science, reproducibility, and education. Yeah, a lot of people involved in the development. So I just want to show you this, but skip it if you want to read the initial paper of it here. And yeah. There should be more forks and citations now of paper. Forks means copies on GitHub of people that do development. So that's also quite nice. Really, if you plan to contribute to MATLAB or to start with GitHub, is the first place for you.
Niklas,
You see, there's a lot of.
Sorry if I interrupt you, but we have some problem, probably due to the connection. We lost him.
Yeah, I'm back. I'm sorry.
Oh, okay. Maybe if you just switch your camera and.
I think it's just like that. It's not even the camera. It's just that the Wi-Fi sometimes just
Okay.
skips.
But now we can hear you well.
Good. What was the last slide you saw?
You have to share the screen again.
So good. Did you see this?
This
Good.
was the last one. Yes.
Good. Yeah.
Yes.
So what I was just saying is that by now we have quite a lot. There's something in the chat. Good. Perfect. So by now, yes, we have quite a lot of forks. So mean developers working with MATLAB. So that's kind of copies of whole MATLAB for your own development purposes that you can do on GitHub. And I think the citations also have increased. I think this whole slide was the state of last year, so should be a little bit more. And that's quite nice after starting this whole thing, like the first commit in 2015. You see users are distributed all over the world. I think by now we also have someone in Africa, so the continents are pretty much covered now. Yeah, and if you want to do developments, so GitHub should really be your first place to start. So you see there's a lot of issues, so people reporting issues. We try to answer. There are some kind of lengthy discussions going on. There you see also some external and internal developments in pull requests here, which we have to admit we kind of work on quite slowly. And there's discussions going on, and there is a wiki which explains a lot about the internal workings of MATLAB. It's not always fully up to date with the current code changes, but it really explains the initial ideas of how the data structures are designed and how the workflow is designed. So this is really the first place to go. Of course, you can also go to the code, and then you see all the development and development branches. And if you are familiar with Git, that's really should be your initial starting point to start working with MATLAB. Yes. So I will kind of skip these details for now so that we get working. But in the current release, we basically have 3D dose calculation with pencil beam and some Monte Carlo interfaces for photon and protons and biological planning. So with constant RBE for protons and biological effect, we have base data of generic machines, and yeah, we can do inverse planning. Yes, and the main important thing about MATLAB when you work with it, especially when you work with MATLAB, like when you work with the standalone, you cannot really do this, but that's also the reason why we use MATLAB, is this duality between scripting and graphical user interface. So MATLAB, the MATLAB programming environment makes it very convenient to kind of look at variables, change variables interactively while you are coding. So you really can use the graphical user interface, write a command in a script, then check the variable as it was created in the MATLAB workspace, edit its value or modify it further by commands to the command line and so on. So that was one reason why we chose MATLAB. The other one was just that it was very popular in the medical physics community. And so a lot of scripts were already available in-house. Okay, here is kind of the proof that what we are doing is not just some random stuff, but that it really creates clinical dose distributions. So here we validated all calculations against clinical algorithms. So here PDC++ is a photon dose calculation algorithm that was used clinically, and Syngo was the treatment planning system at HITR. They switched now to another commercial one. But you see that kind of these differences are really minimal in dose, and that we create clinically relevant dose distributions with MATLAB. Yeah, that's the user interface that we will check out later. So that's how it looks like. I will explain everything about this soon. But before we get to this, I want to quickly, because you may be also interested in research projects, or you're doing your PhD, and I don't know, you are working on helium planning, so you might be interested in doing some helium dose calculations. So there is a research branch which you find when you go on GitHub, where you can do this with a very simplified biological model for biological planning as well. For example, you might to do robust and probabilistic optimization or uncertainty quantification. So there's also this branch, you see, it seems to be quite heavy and have a lot of developments on it, and that will also be in the next release. Or you might be interested in variable RBE and effect for protons. That's also on there. Yeah, and here we are trying to build a new graphical user interface as well that then can also be used with some limitations with Octave. So maybe you want to check out this, but that's also under heavy development at the moment. Want to check out more of Monte Carlo interfaces? That's, for example, on this branch, but that's also a little bit outdated because most of this has already been merged in this giant branch here towards the new release. So we have some research projects which we usually then have under research/project. So for example, research superiorization, which is a kind of optimization method. And we also have some external contributions on branches like VMAT and ExactOp. So these might also be interesting, but what you see is that when you are interested in more functionalities, it's a chance that they are already there and just hidden in some branch. In this case, you just write an issue on GitHub, and then we can maybe point you towards the right branch if the development is already there. So the most asked things are usually, do you have Monte Carlo? More Monte Carlo? Is there a Topaz interface? Like some DICOM stuff, VMAT is often asked. So this stuff, there's a chance it's already there, and you just need to ask us on GitHub. Yes, here's kind of a feature list that I won't go through now, but you have this, I think it should be now as a PDF in the Indico. And yeah, that's basically also, and should also be on the Indico, is the exercise that you should later hand in. And in principle, this is like a kind of a very easy thing. So shouldn't take too long of a time. So even if you have issues with the installation and you just manage afterwards, this can be done in, let's say, less than an hour. Probably even faster. So I can probably do it in 20 minutes or less. So that's basically only limited by the computation time. But what you should be able afterwards, at least, is to create plans for photons, protons, and carbon ions, and compare them by exporting those slices and those volume histograms. And you can use for the exercise any of the above data sets. So the first ones, Box Phantom and TG119, are really just phantoms or water boxes. They are very easy to understand. So if you basically really want a very simple case, you go with the phantoms, but you can also look at liver, head and neck, or prostate. But I would be careful a little bit if your system is limited. I would maybe not go for head and neck and prostate because they are kind of large. Like the head and neck is very large, the prostate is medium large, and the liver has a smaller target volume. So if your computer is like it's a private laptop that is not very powerful, I would maybe go with the liver. And if you have, I don't know, sit at a workstation, you can also go with head and neck or prostate. Okay, so that's the exercise for the end. And yeah, any questions so far? I'm quickly stopping. Is there any questions?
No, it seems that everything is clear, Niklas.
Good.
Great.
So yeah, the data sets, I got like a direct message where
Okay.
the data sets are. So it's good to just ask these questions to all. So maybe people can help. So I will show it soon when we start up Madrat. They are a little bit hidden when you have it installed on Windows. That's a little bit the issue. When you install the standalone and have it on Windows, it's a little bit, but we will figure it out. I just want to say one more thing. So there's also these workflow documents, right? The 3 workflows from the last school, which were basically pure planning exercises. That's the treatment planning with Madrat on, like, let's say the Tuesday, Wednesday, and Thursday documents. You can really, like, after this course, and if you want to give courses in particular, so if you then want to show your students how to give like how to do some treatment planning, these workflows should be doable for you. So that's really then something that you could consider as course material if you're interested in comparing photons, protons, and carbon ions. So what is particularly covered in these workflows, I will maybe quickly share my screen again so we can, so I need to stop the presentation. So that's so they are kind of grouped. So the Tuesday is kind of going from the classical photon therapy to in the end proton therapy and to the first real patient case. So it starts off with a phantom, like with a C-shaped phantom wrapped around an organ at risk, and goes towards the prostate case and trying to make the first treatment plan. The second one deals with one of the, let's say, major difficulties in treatment planning with particles. So it's called a glimpse at uncertainties. So it will take a look at how treatment plans and dose distributions behave in case the patient is, for example, misaligned, or the underlying quantities for dose calculation, like the electron density, or more exactly the relative stopping power, are not accurately defined, and then it will compute. Here in this exercise, you will recompute with a shift of a few millimeters, and further down you will do density scaling to see how this affects the treatment plan. And the third one is fully about biological treatment planning. So there we really start to check out how constant RBE and variable RBE in carbon ions, which is then further down where we optimize with the LAMP4 model, how this is affecting those distributions. We will try to take a glimpse of most of this today, and we'll just show you how to set this up. And then you should be able to also give these courses in the future. Okay, so now I think we can go towards working with MATRAT. So first of all, when you have installed MATRAT as a standalone, so you should somewhere, like on Windows, you should somewhere have a like a MATRAT button, for example, on your desktop. I copied this one into a folder here. So you should somewhere have this MATRAT button. And if you have installed it on a Mac, you should have, it should be now in your applications folder. And if you have installed it on Linux, you should probably know where it is. I always expect if you use Linux, then there's a little bit more, it's not fair to assume that, but there's a little bit more nerdiness involved, and that you are usually able to navigate with the paths and stuff like this yourself. So the Linux support is quite limited. We have it running on Linux, but since there are so many different Linux-based variations, it's sometimes a little bit challenging to then have like an easygoing instruction set there. So if you work on Linux, I hope you figured it out yourself. But so when you have it installed on Windows, you should be just able to start it like this. So I will quickly start the standalone now. And after we have started successfully the standalone and loaded a patient, then I will change to the version from the code, and I will work from this, and the rest of you can just follow with all the user interface interaction. So basically the user interface should just start up like this. It should be like this white empty canvas with a few parameters. Okay, so now the question was how to find the patient data. And I think on Mac and Linux, it is quite clear. So on Mac, it should be in the applications folder, basically where you have MATRAT installed. But on Windows, it's also a little bit hidden because MATRAT is installed under program files, as most of the programs usually. So when you have installed MATRAT under program files, or like basically, I think it's even the same on Mac, the MAT files, so the pre-stored phantoms that we can use for this course, they are usually in the installation folder in the folder application. So for example, on my system, MATRAT has been installed in C program files MATRAT, and then there's a few folders, like folder kind of some standard files, and there's a folder phantoms.
Niklas, we have lost you for a few seconds.
Okay, sorry. So just again, yeah, I see now it says that it's slightly unstable. But I should be back now, hopefully. So
Yes, it's okay.
so the phantoms, so the MAT files which contain the CTs for planning, they are in your installation folder. So on my computer, like MATRAT installed to C program files MATRAT. Okay, and there you have 4 weird folders: app data, application sys uninstall, and within the application folder, there you find the executable and also a phantoms folder. And in this folder, you have your MAT files. Okay. So let's maybe copy this from here. So when you are in MATRAT, the first thing to do is to load data. And since we are now not working with an independent DICOM dataset or some binary CTs that are stored, for example, in MHA or NERD or whatsoever, we choose load MAT data, and often this starts in like the latest folder you had or similar. So then you just navigate to this folder here. So for me, as I said, program files, MATRAT application phantoms, and there you have all the phantoms. Since we only have like this course and basically not too much time, I would really directly start to use in this course the liver patient. I like the liver patient. It's not too big. It's a little bit interesting with selecting angles. So let's start with the liver patient. You can just click this and then it will take a while and it should load the patient. Okay. I hope it loads the patient. Yeah, it does. It just takes a while. Good. And then you see the patient. So I will now stop to use this standalone, and I will show you, if you work with MATLAB, how to do the same thing there. So I'm closing MATLAB right now, and I'm basically going to MATLAB. So yeah, so you launch MATLAB, and the first important thing is, I will just clear everything so that I have a clear session so that we do all the same thing. Good. Now everything should be cleared. So when you navigate into this folder, so for me, it's indeed temporary MATRAT 2.10.1. So that's where I extracted the code to. Then you see all the code here in the left side. And I think I showed this yesterday already. We now need to initialize MATRAT. So the first sensible thing, you can either directly start the GUI, the graphical user interface like this. But what I tend to do is always run this configuration script, matrat_rc, like this, because then it shows me which version I'm using, which MATLAB version I'm using. Sometimes quite helpful to see once more and have a clean start here. And after this, you can start the graphical user interface with this command. So matrat GUI, and this starts the user interface, and then you have the same starting point, let's say, as the people with the standalone. So when you just work with the standalone, you have the same features as a programmer just working with this matrat GUI command and then working with the user interface. So what I can do is that I could now load this data as well from here. But when I work with the code, I can, and that's kind of the first thing of this duality between code and graphical user interface, I do not need the user interface for that. For example, I could just do this. I load liver.mat. And then maybe the first interesting thing is that the variables kind of appear directly here in the MATLAB workspace. So there is the CT variable, which is the structure containing all CT information. And there is the CST, which is a remnant of a previous DKFZ in-house system, which means the constraint structure tree or something like this. So I don't even remember anymore what it means exactly. But this here contains all the CT information. And the nice thing here in MATLAB is that you can just click on it and then you get the variable editor and really see how the data structure here looks like. So you see there are the cubes stored, one in Hounsfield units, the other one is already converted to some water equivalent path lengths, but this one is the important one in Hounsfield units. There is some DICOM information of the import stored with it, the dimensionality, so the liver patient that is stored here in a somewhat lower resolution of 217 times 217 times 168 voxels and so on. So you can really start to just look at the data. For example, the resolution is 3 millimeter in X and Y and 2.5 in Z. So that's quite nice to get some information. And for the CST contains the structures. So you can look at it and see, okay, there seems to be a GTV, which is a target volume. There seem to be organs at risk, which are named by OAR. Yeah, so you really directly have access to everything. So for example, if I would now want to know what this fifth column means, I could in the code also just check out what's here in this column, and I would see that it has some parameters for, let's maybe switch this up, has some parameters available, like there's some alpha and beta ratios for the biology. So the alpha seems to be 0.1, the beta seems to be 0.05. There's a color encoded and so on. So this is quite helpful to just work with this. One thing that you always find in the workspace, which is sometimes quite interesting, is this MATRAT CFG. This MATRAT CFG always holds the configuration information of your current MATRAT session. So it kind of shows you which folder you has some values and so on. So that's quite helpful for some global configuration and in checking this out when you do search. Connection is unstable. Do you still hear me?
Now, yes.
It goes and comes.
Go ahead, Nicholas.
Niklas?
We lost him.
Yeah, we definitely lost him.
Didn't really. Now it's.
Yeah, I think that she get out and probably he will try to get in again.
So far, people can follow. How is the level? It's okay? Yeah.
Okay.
You can get an idea. Okay, perfect. Hi
Yeah.
again,
Sorry
Nicholas.
again. Yeah, it's
Yes.
like
Okay.
really. It's just kind of like every half an hour it seems to cut out. I don't know why. I realized this
And yeah.
yesterday. I tried it with Netflix a little bit, but okay.
Niklas,
That's
in the meanwhile, we asked to the student if they are able to follow you and everything is under control. So
good. Perfect.
yeah.
So yeah, I will go back to sharing then. Okay. So yeah, that's kind of how this works. And the nice thing is, so if you haven't followed the last bit about some of the data structures, not as important. The main thing is you have this parallel available. And the nice thing is now you have loaded the data, and in principle, you can go back to the user interface and just hit refresh. And now it takes a while, and the user interface always works with the data that which is available in the workspace. And it will realize there is a patient loaded, and it will have it there as well. So really you can just load data, then update the user interface, change some parameters and so on. So I will spend more time on this now in the beginning. So the standalone users might be bored now. So I'm sorry for that, but I really just want to show this in the beginning a little bit how this works. Yeah. So now we can check out what tools we actually have here. So in the top where we clicked to load the data and the refresh, that's what we call the workflow widget. So in the workflow widget, you can basically from left to right, let's say, in a sense, go through the workflow. What means in left to right? So the left column here is data import. This one is dose calculation. This one is to optimize the dose or recalculate the dose after changing parameters with the same optimized fluences. And the last one is to export data. So that's kind of the workflow you can go through, right? From left to right. Then you have plan parameters that you set. So plan parameters need to be set optimally in the beginning before you start going through those. You also see that in the beginning only calculate the dose, so the influence matrix calculation. If you follow the treatment planning lecture, you should know what an influence matrix is and that we need it for planning, a dose influence matrix. So these parameters are optimally set before you start the whole dose calculation optimization process. So if you change them when you already optimized, usually the optimize button will gray out and it will ask you to calculate dose again because you changed the irradiation geometry. But here you can set like parameters, like something that we call the pixel width, which is either like, let's say in photon world, it's the width of a fluence element, like a beamlet, and in the particle world, it's the distance between adjacent spots or many like pencil beam Bragg peaks. Then you have gantry angles that you can select. So gantry angles of the rotating gantry around the patients. So when I said visualize plan here, for example, below, then you see what the gantry angle is. So it's basically at the moment there's the 0-degree gantry angle, 0-degree couch angle, meaning the beam would just come in from the top here. You can set the radiation mode in the machine here. So you usually, so MATRAD always includes a generic machine, but you can also create your own machine data. We will look later a little bit on how, for example, a proton machine looks like in MATRAD. Here you can set the radiation mode between photons, protons, and carbons. That's the modalities included in the release. Here you see the isocenter, meaning the center of rotation. So that's basically your whole geometry rotates around this point in a sense. And you see it's marked also with an X in the plan. That's what this X stands for. You can say the number, define the number of fractions, and this is quite important because MATRAD, when you prescribe doses for the optimization, it always takes the total dose, but unfortunately for some decision that we had like 5 years back, it then shows fraction dose as the result. That's because for RBE weighted dose does make sense in a fraction and not that much as a total dose accumulated over all fractions. So that's a little bit challenging, but we will see this later. And then you have here some options which are mainly for photon dose. So you can simulate a not intensity modulated treatment with 3D conformal. You can turn on the MLC sequencing, so the generation of multiple shapes to modulate the fluence here, and can set the number of shapes, and you can do direct aperture optimization. So this is not very important for courses or so, but sometimes when you want to create a deliverable fluence, you might want to run sequencing. Conformal is sometimes useful in a course because it really shows you the oldest way of computerized treatment planning, where you really just had open fields and tried to shape them accordingly in photon therapy. But yeah, I won't go too much into detail there. You can find some information on the wiki. So the next, or maybe before we go here, I want to basically show you, after we refreshed this plan here in the graphical user interface. So that's for the MATLAB users. All this plan information actually has been encoded in another structure, which is very important in MATLAB, which is the PLN structure. So for example, all of the information like the gantry angle is now encoded here in this plan structure, in this property STF. So you see pixel width, gantry angles, couch angles. And again, you could change something here. So I could change the gantry angle here now to 90 degrees, right? So I could just modify this as I please. When I look back into my, user interface and hit refresh, will take a while, and now have the 90-degree angle stored. So you can really work in both ways at the same time. So that's just for showing how this works a little bit. So the plan structure encodes everything that's given here, plus some background information as well. There are some hidden parameters in the plan structure that are not specified here for simplicity of the user interface. So you might be, it might be very useful to take a look at the wiki or even at the code in the end to figure out which parameters are used where. We try to, with the next release, we will try to expand the documentation there a little bit so these parameters are clear. But for now, you also have to live with some of these parameters being hidden. What you can also do to figure out the hidden parameters is going to this MATLAB CFG structure here, or object. And then you could, for example, look at prop STF, and then it gives you a lot of default parameters. So for example, for protons, there's a default longitudinal spot spacing as well, which controls the energy selections. And if you want to add a margin when you distribute beamlets and so on. So there are some hidden parameters here, which are not provided in the user interface. Okay, so that's basic information about setting the plan. The next one is the objectives and constraints tab, and that's very interesting for treatment planning. So the objectives and constraints tab allows you to set, basically design your optimization problem for treatment planning, and it uses the weighted sum of objectives approach subject to constraints. So that should also have been discussed in the treatment planning lecture. So what you really do is that you piece together your objective function out of building blocks. So at the moment, we have an objective on the PTV. The PTV is here for this liver patient. The target volume, it's given in, what is this, violet color, like this here. You see it includes a CTV here. and a GTV here. So the GTV is the tumor volume you would actually see during all the imaging before planning. The CTV is what the clinician would say there is to expect some infiltration of the tissue, and the PTV tries to cover uncertainties. So basically that's your setup, and at the moment we only have an objective on the PTV and an objective on the skin, which means on all the other tissue around it. That's the simplest setup. It doesn't care for any organ specifically. It really just tries to minimize those to a certain extent in the healthy tissue and reach a dose level in the tumor tissue. So yeah, that's what's also encoded here in these functions. So the skin has a function which is called squared overdosing. So it penalizes overdose with respect to a certain maximum dose, which is here given as 25 gray in 30 fractions. So 25 divided by 30 per fraction. So this dose level will be, like every dose voxel that violates 25 gray will be penalized in the optimization by squaring the difference. And squared deviation will kind of penalize all differences to 45 gray within the PTV. And the P here is the penalty, the weight that you multiply with this. So this objective function would actually be 300, then there's divided by number of voxel, but that's not important, but 300 times dose minus 25 if positive squared. This objective would be 1000 times dose minus 45 squared. Okay? But this one penalizes overdosage. This tries to reach a prescribed dose level. And there's a lot of other functions that you can choose. All of these here are objectives. So here, for example, you can optimize the equivalent uniform dose. You can optimize a DVH point, min DVH, max DVH. You can minimize the mean dose. You can only penalize underdosage. So for example, for a tumor, it might also make sense to just to not be as strict on underdosing. So you would choose an underdosing objective here, okay? Then you can check the parameters. Might want to go back to 45. I think 45 is the preset value here. And then you could add another objective, which you can do here to the PTV, let's say here, plus, and there you could now only penalize overdosage, be a little bit less strict on this, and have, I don't know, maybe 50. So now you would allow the optimizer to distribute dose between 45 and 50 gray freely, penalize underdosage stronger than overdosage, and so on. So that's how you can piece together your optimization problem here. Okay. But I will go now back to this one. Okay, so that was the initial setting. So from the treatment planning perspective, what we miss here is organs at risk. So let's quickly take a look at the liver patient. So let's quickly skip to the right side. So we see the CT with the Hounsfield unit scale on the right. We are in one slice, which is given here. It's actually the isocenter slice that Madras selects by default. You can, on the right side, control a little bit the graphics or the color scale. So for example, you could switch to a different preset. For example, would go here. There's a liver preset. Let's see how it looks like. This looks, I think, okay, but very contrasty. So it has a very narrow window now of values that really mean something. So for example, you could also check out this preset. It's a little bit different window. So it depends on what kind of CT you want to watch, but you can all change this here. You could also choose a different color map, like not the bone, but natural gray, jet, I don't know, whatever is beautiful to you, use it, but usually you take this bone color map for CT display. You see also, you can also scroll through this. I have like my laptop here, so I'm a little bit, it's not very easy, but you can scroll basically with the mouse wheel or the scroll function on your, whichever is your scrolling gesture on the pad. So you can scroll through the CT, and there we see kind of quite impressively the liver. We see the heart, right? Quite impressively coming up. It's also clear that we have the spinal cord here. The patient is lying on the table like this. So what you could also do now, because you have a lot of structures here and a lot of helper structures, is, for example, you could remove this dose fall of structure. So the dose fall of structure is a helper volume that allows you to shape the dose gradient, for example. Just clear and get some other volume. The liver CTV, which without the CTV is also helpful, but does this actually automatically. So then you have a little bit, like it's a little bit less cluttered around here, and you quite nicely see the CTV and the PD. Okay.
Niklas?
Again,
Yeah.
Niklas.
Yes, I'm back. I'm back.
Okay.
I can repeat a little bit.
Last minute, please.
Yes. So I think the last minute was not that important, but I can go through it. So the only thing that I explained in the last minute was basically that, oh wait, I want to share my full screen because I switch between applications sometimes, so need to reshare it. Good. So what I wanted to kind of just show is that you can use the structure visibility widget here to turn stuff on and off. Like can remove the liver CTV, for example, which is an helper structure to remove the CTV from the liver for planning. I also remove this dose fall off, but that's not that important. It just allows you to have a little bit cleaner view. So from a treatment planning perspective, what we maybe would like to do here is also spare the heart, and maybe especially for photons where you cannot really control like exit dose that easily and need more gantry angles, you might also specifically spare the spinal cord. So in MATRAD, you could add objectives, and I will do this slowly so you can kind of introduced it before. So you can go to these objectives plane, and then is this drop down menu. You can pop it up, and all these structures that are on the right side and also that you saw earlier in the CSD will be available here. And then you can, for example,
Niklas, we cannot hear you.
No. Oh, you get out. Here, he's back.
I'm sorry, this really seems to now struggle. But I will turn off my camera now. I don't think it will help because it's really just shutting down completely from time to time, but yeah, let's try again. So now I really want to show you how to, no, that's not what I want. This is what I want. Now I really want to show you how to add objectives on the risk organs, the organs at risk, like the heart and the spinal cord. So what you need to do for this is that you go to this objectives and constraints panel, right? Where you can piece together your objective function. So now you can just click on this drop-down menu and, for example, let's select the heart first. You click on plus, and then the heart shows up here. And you will be able to assign an objective to it. MATLAB will usually select a squared overdosing objective directly, which makes some sense. Then you can choose the importance of it. So this might be more like should be at least as important as the skin. We could reduce, or the skin is not really the skin, it's really the whole body contour here. That's a little bit confusing. But we could reduce also the importance of the skin a little bit. So we have nice target coverage. So that's kind of maybe some settings that would make sense here. I set, so usually you would kind of start to now select these parameters from your clinical in-house treatment planning protocol, right? There would be a protocol which tells you how much dose the heart should get at maximum, and so on. So I will now choose any values. For example, I want to have the heart a little bit more relaxed than the skin, the rest of the healthy tissue. And I will do the same for actually the spinal cord. So, or let's take the spinal cord plus 5 millimeter, because we also want to have like be safe with some margin, because the spinal cord is a serial organ. That means if you damage it at one point, you kind of lose the whole downstream of this point. So it doesn't help that you save 99% of the spinal cord if you kind of kill one layer somewhere on top. So there you would be a little bit more sensible, or like a little bit more sensitive with your optimization and planning choices. But yeah, you can kind of just design your problem, could be even stricter here with the maximum dose. So that's just how to piece it together. And that's also a very nice treatment planning exercise to do, to change these parameters and see what the outcome is. Okay, so that's really what I want to spend on treatment planning. I think you're all advanced students, and with the workflows and with some playing around and so on, you will figure out kind of the rest and figure out how this works. And what I wanted to quickly show you is that this, of course, is now also stored in the code, basically, or in the environment of MATLAB. These data structures must be somewhere available. And if you remember correctly, that's the CST variable where everything is. And you see that in the 6th column, so we got some more information here, but especially in the 6th column of the heart, you now have additional structures that just store all this optimization information. So you could also create your objectives here. And what you also see is that it kind of pre-computed contours and stored this, which is not so important, but just to show you always that this is basically in the back and can be modified from. That's everything I want to this object mouse could play this when you have the time. What objectives and constraints are called house if you have some So
Niklas, I have to interrupt you again because we lost something. Okay, we lost you.
Meantime, if there are questions, maybe everybody
are
can
there
type.
questions?
Yes.
Before we go to dose calculation and optimization itself and look at the different modalities, are there questions?
It seems not.
There's one, yes.
Yeah.
It's a rather easy one. Maybe you mentioned it, but maybe I missed it. Is it also possible for us to do our own sort of optimization structures, like the ones to help out the optimization, like some rings or?
Yeah, so it's in principle it's possible, but it's not implemented as an easy tool. So when we do it, we usually, so for example, what you can do is quite with some coding. So we only do with some coding so that you subtract like the one mask of the other. Or stuff like this, or that you create a margin. There's a function in MATLAB for this to do it, but we haven't coded it in the user interface because we say, yeah, for contouring and so on, there are so many amazing tools, right? You can start Slicer, or you can start MITK, sorry, and so on. Yeah. Okay. So it's not in the user interface, but you can use the image processing functionalities of MATLAB to do it. I can maybe really quickly show this or basically tell you this. So in the CST structure, there's all the voxel information of the structures encoded as well. That can be found in the wiki, and then you can modify this or create new lines there in the CST. You can just basically create a line, assign voxels to it, and that's a new organ. It's really, but there's nothing in the user interface that helps you easily do it. So there's no contouring functionality because it's kind of extreme overhead to implement in MATLAB, and MATLAB is not that fast, and there's all these auto segmentation tools now and whatsoever.
Okay.
Good. We have another question, which is
There
about the
two,
optimization penalties. So yes, it's about basically deciding these functions, and deciding these functions usually is based on in-house protocols. So for example, when you work as a treatment planner, you will get a protocol which says the target should, like 95% of the target volume should be covered with a specific dose. Then you will, it's a lot of experience to then select these functions correctly. So you will select functions that pull you towards these values. You will select a function that penalizes under dosage for the targets. And then for the organ, you will have maybe a protocol that says, like, the maximum dose in the spinal cord should not exceed 40 gray in 30 fractions or whatsoever. And then you have to choose functions that pull the dose below 40 gray. Right, so that's kind of given by the protocol, and that's how you piece them together. In a really modern treatment planning system, they will store kind of atlases of previous plans, and will try to give you suggestions for this, for example, or they will work with even more fancy machine learning tools now. There's quite some interesting stuff there to reduce the workload on this choosing of the objectives. So yeah. So there's like other files. Can we import DICOM? Yes, you can import DICOM. It's not guaranteed to work. There's a load DICOM button if you saw it. Then is there a database of cross-sections, of inelastic cross-sections? No. maybe almost. So MATROT has an interface to MC square, and MC square has a table of some cross sections, I think somewhere stored. And we also have a Topaz interface. And so, for example, you can look at Monte Carlo. If you want a table of inelastic cross sections or something like this, then you would go to a Monte Carlo algorithm. MATROT itself doesn't have it. Yeah, and the organ motion in MATROT, so that's quite detailed now, how to set up organ motion for a particular setting. So usually for the motion you will add a margin, right? So that's one way to do it, or you will do robust optimization. I won't go into these details today because kind of at some point I really want to get you to the basics of the three modalities, and we cannot look into robust optimization or advanced margin definition. But in principle, you can create a margin with MATROT by code, or you create a margin in a different software and import it. So yeah.
Yeah, I was like particularly considering the breast cancer, and like you know, when you are planning with photons, you are going to consider the flash margin just to take into account that the patient is breathing. So in order to take into account this motion, we consider like 3 centimeter flash margin. Like, so I wanted to know if I missed, for example, if there is a way in MATROT thanks to which I can like set this flash margin.
Not in the version you are currently working with.
Okay.
There is a kind of, so there is a function which allows you to specify a margin around a structure with basically saying in X direction 5 millimeter, in Z direction a centimeter or something like this. But in this version, it's not yet in the user interface, but the function is basically called MATROT add margin.
Okay, that's fine. Okay, thank you.
So this works, but yeah, like the margin setting is a little bit, so we usually expect the margins to already be there in the user interface or create them in the background manually.
Okay,
So,
thank you.
good. Okay. Then I guess I will continue with with creating a treatment plan. And first, so I hope it doesn't cut out again, but let's share the screen again. Good. Here. So we will really do, like, I know we are in the heavy ion school, but we will start with a photon treatment plan because it's the, let's say, most used modality. It's always good to show later why particles are used when we have a photon plan ready. And MATROT is a little bit, let's say, very basic when choosing gantry angles. So I will choose a 5-beam photon plan very quickly now by choosing 5 equidistantly spaced beams. And what you need to do in MATROT for this is actually to just type in the gantry angles one after each other in the user interface. So I will choose gantry angles with 72 angles apart. So because I do this all the time, and then I know the values, and you really need to make sure that you have as many gantry angles as couch angles. It's a very simplified process, but then you should end up with this configuration. For example, you can also choose a different configuration. So you do not have to follow the same configuration I do, but yeah, just choose some gantry angles and start with this. You see that not much changes around here. Like basically you don't need to change anything else. You should make sure that your radiation mode is set to photons. And yeah, I basically just leave everything else. So maybe, yeah, we will go to this lower section, the visualization section later. But what you do after setting all these parameters is that you go to your next step in the workflow, and click on this Calculate Influence Matrix button. So let's do it. It will load a little bit, and then it will start computing the dose. So it's a photon plan. It's not a super fast dose calculation algorithm. As I said before, we do not have the time to optimize extremely for performance. I also have to say that when we programmed MATRAD initially in 2017 or 2015, actually these runtimes were quite competitive for the treatment planning system, but now they are they have so much optimization in their code that they become much faster. So the error that you might get is when you do not have the same amount of gantry angles as couch angles, then it will say, I cannot optimize or cannot calculate those. So you really need to make sure that if you have 5 angles here in gantry angle, you need 5 angles here as well. So in the masterclass version that we often use, we kind of remove the couch angle, because I usually never do them in courses, because it's a little bit unintuitive in the beginning for students that don't know much about treatment planning. But the couch angle is like rotating the couch, and I'm just going with zeros now for simplicity. So, all right, so we now calculated the dose influence matrix, and it doesn't show us dose yet. Why? Because we don't have machine fluences yet for this dose. So now we only have computed the influence of each individual small beam sub-element normalized to some value to the CT. So we don't have any dose yet because we don't have any optimized machine fluence. But I want to show the people that work with the code some interesting stuff that you can do now to figure out, to learn something about the dose influence matrix. So let's go back to MATLAB quickly. So let's say, and that's, for example, a use case I also see sometimes in MATLAB. Let's say you have an external tool to compute with which you want to compute the dose. So let's say you have Luca or something like this, or you have like your own GN4 based code or whatsoever, you have Topaz installed. You still hear me? Yes, I just sometimes, I'm kind of checking a little bit if I see Jota moving, and then I know I'm still I'm still online. So for example, you might want to move the dose calculation to another tool and then load it back into MATLAB. And so what we see is that there are basically 2 new exciting data structures popped up after dose calculation. The one is the STF, and the STF is something that means or is called the steering file or steering information. And the STF contains for each gantry angle all the geometrical information. So which angle it is, what is the mode, what is the source to axis distance, how many lateral beamlet rays do we have, and so on. So this is like really, you get all the geometrical information. For example, here you see like that one is looking at the isocenter, it's 40 millimeters to the left, and so on. So this really holds all the geometrical information. And for example, for our Monte Carlo codes that you can only call by code, by the way, not from the user interface yet in this release. For this, we use these information passes to the Monte Carlo. If you really need to modify, for example, the guide implement.
We are losing you, Niklas. Niklas?
Yes.
Yes, now
I
we
see you
hear
moving,
you.
but I think going to
Yes.
cut out soon, probably. Let's take it, take a short pause.
meantime, I could point out, as Nicholas said, that there is a very simplified version, a reduced version, executable, that we use for the particle therapy master classes. And
So I'm back,
yes.
but I paused, I think, on time.
Yes. So Nicholas, when you will be showing, maybe you can point out in the graphical interface afterwards what we tell to the students that in the reduced version. You kind
Yes.
of made already a comment about that.
Yes.
Of course, this is for everybody to know how it works, but when we do the particle therapy masterclass, we really keep it simple. Yeah.
Yes, yes, of course. But this should basically show both. So I will just want to go to the data structures. And the other important new data structure is the DIJ, which contains all the dose information. So this really shows you what was the dose grid we calculated on and so on. So you can learn about this in the wiki. And the exciting thing is the dose matrix. The dose matrix is stored here. So it's really a matrix, number of voxels, number of beamlets. So this is quite big. It's sparse. So we really can take a look at how much those values are actually non-zero there. So this shows you a little bit how you can interact with the data structure a little bit. And then you see that, so let's see, 60 million entries are non-zero here. And yeah, you can kind of divide this maybe by the number of elements in the whole matrix. And then you see that's quite a slow number actually. It's actually only 1% of the values really have those. So you don't need to store this, all of this giant matrix, you only store a subset of it. So that's maybe just like, that's how you can interact with the data structures, can use them also to extract information to show to students. But now let's go back to the user interface, because you really do not have this information available in the standalone. It's kind of hidden. What you can do, I'm not sure, I can try it. Let's try to compute the 3D view. So I can maybe show you the whole thing in 3D and then you see this information. At least the steering information a little bit more relaxed. Yeah. So as Jutta said, for the master class, you will not have access to these data structures. But for the researchers among you who want to consider using it also as a toolbox for scripting, for example, this is, I think, necessary information. So what we see now is the whole thing in 3D. And if I click on visualize plan beams, well, let's check this out, then you actually see now the steering information of how MATRED kind of distributed this or created this field. So it shaped them already conformal to the target projection. So you see there's kind of the tumor shape here. Can also rotate a little bit to see they are all looking a little bit different, right? So that's kind of what's stored in the STF, exactly how these beams are aligned. But I will close this for now. Always be careful with the Open 3D View button. There are sometimes structures that MATLAB, for some reason, has problems with to render them in 3D, and then it can take quite a while. Especially if you have geometrically very clean structures like boxes or something like this, it kind of gets sometimes problematic to compute the right polygons with MATLAB. So yeah, that was just a quick showing. And now we go directly to the next step. You also see, by the way, now nicely the star-shaped equidistant beams. Maybe this beam is not the best choice because it directly goes to the spinal cord. So, but I think we can also check now how the optimizer deals with this. And so we go to the next step in the workflow after those influence matrix calculation. We now optimize. Good. And the optimization will take a while to initialize usually. In this release, there still like quite some overhead in the initialization. will be cleaned in the next one. And yeah, what now happens is that we just minimize this piece together objective function that we have kind of written down as these building blocks down here. So the optimizer takes this, creates a sum, multiplies it by these p's. I think there was a question on how to select them. Yes, that's the big question in a sense. How do you balance targets and organs against each other? So this is all encoded in these penalties. There are also modern optimizers which don't really use penalties. They create multiple plans with different trade-offs and scale between them then manually, or you can scale between them. But these penalties, the selection is kind of experience. It's a lot of things. It's experience, intent of the treatment. So if you really need to cover the tumor, you would take high penalties. If it's a palliative treatment, you would maybe sacrifice more coverage and so on. So actually, I optimize now. The plan is very bad because I just put in any values here. So I haven't thought about the values beforehand. So the optimizer now had to really actually put a lot of effort into sparing the heart, or maybe too much effort, also a lot of effort into sparing the organ at risk. So it created a very strong hotspot here because there was nothing much to penalize, because the skin was actually very, like the rest of the tissue was very penalized, very relaxed. And here we come back to the question, what would you do now in terms of treatment planning or penalty selection? So for example, you would now do a second optimization where you would maybe reduce the penalty on the heart a little bit to allow to not force the optimizer to create such a hotspot here and so on. So I don't go into detail here, but you could now modify these penalties, re-optimize, modify the penalty again, re-optimize, and so on until you have a nice plan. But that's not really the goal, at least for today. So yes, now I want to go to like, especially if you give a course, these are very important tools when you have made a plan. When you do research, you usually do analysis a little bit different, right? You have your evaluation scripts then in the end that extract the data that you need. But for example, also for your exercise, in the end, when you give a course, you want the students to somewhat like export some data, right? They should have some images available. And there's a few ways you can do this. So there's 3 important things. The first important thing that people can always do, or students when they work with this, they can save their current plan, right? So there's a button which is called Save to GUI. So there was a question in the chat on how to see these angles in the image, and you can enable this by this button, Visualize Plan/beams below here. So just for quick answering this question. And yeah, don't hesitate to write Noah if he is still here. Also messages about this. Okay, and yeah, so there's one button which is quite important for the masterclass. This is the Save to GUI button, which allows you to store a plan for later selection. So you can call this first plan, for example, Photon 5. Okay. Clicking on the Save to GUI button and then save. And then this plan will, for the future, until you completely reset Madrat, be available here in this display option tab. So what you see that this plan is now available as physical dose plan. You also see there's actually some other nice things to look at. So for example, I could only look at the dose from the first beam, which kind of also shows you that it has a big part in creating this hotspot. But that's quite nice because then you can do comparison studies in one sitting with the students, for example. You can say, okay, I have created my first photon plan. It's the photon 5 plan. What you can also do is you can export those slices. So you can, so that's the most hidden button probably of all. It's the screenshot button, which is this camera up here. Okay, up left next to the save button, there's this camera button. And if you click on it, basically you can just export a PNG of your plan. Okay, so that's helpful for the exercises. So you could export a PNG like this. What you can also do is, after you click on it, cancel it. So for me, it is in German, speichern, abbrechen, but if you cancel it, you will basically see the whole figure, right? Like this. And this is what will be exported, and then you can save it manually from here. Good. That's the two most important things: to store the dose and to export the dose for the students when you give courses or also for your exercises. There's another important tool, and that's how to analyze the plan, okay? So how do we analyze the plan? So there's SmartWord is in the user interface, kind of has this one button which allows you to show a dose volume histogram and quality indicators. It's below in this visualization tab, show DVH QI, right? When you click on it, it will take a while, and SmartWord will compute a dose volume histogram together with associated quality indicators. So it will pop up a new window, and let's open this. So what you see here, it will create for every active organ at risk, it will create the dose volume histogram. So what you see is now kind of here, for example, the dose volume histogram to the PTV, and it might have maybe make sense to disable these clips before, because they are only one voxel element somewhere in the target, I think. So they are always kind of very perfectly covered. But here you see the PTV in the background. Yeah, maybe let's quickly do this. Let's quickly disable the clips here on the right side and kind of disable these clips as organs. And then you can click show DVH again. It's not important if you keep the clips active for later submitting an exercise, but now you see the DVH is it's a little bit cleaner. You see the CTV DVH shows very nice coverage. Remember, it was 45 gray and 30 fractions, and now we are at 1.5 gray and 1 fraction, what this kind of means. And you see that actually kind of, for an unrealistic treatment plan, the DVH looks actually somewhat good, but you saw this hotspot on the photon side. That was not so good. You see a lot of statistics here. I won't go into detail what they all mean. So if you know it, you know it. But the most important also in courses that I usually look at are just the standard statistics. That's, I think, for most students easy to understand what a maximum and a minimum and maybe an average dose and a standard deviation of the dose is. And then you can kind of just check all these values out and also let, for example, students report values here. So what's the maximum dose in the liver? What's the maximum dose in the heart? What's the maximum dose in the spinal cord, and so on. You can also save this from here. I think it should be exportable. You shouldn't save it as a MATLAB figure, but you can also save it as a PNG, for example, from here. Okay. So that's the important analysis tools: storing or caching the plan with the save to GUI, create screenshots with this button here, and show the DVH. If you are doing research, you can now, for example, now go to the exporter to export CT, dose, and so on to some binary format and load it somewhere else. Or you could import a reference dose in a binary format. It needs to have the same resolution, I think, at the moment. But that would be possible as well. So just if you are interested here to do this. So now, so that we also see the other modalities active in MATRAT, you can kind of very easily just switch the modality and create a new plan. So that's, I think, as soon as you have understood the workflow for photons, you can now also go to protons and carbon ions and basically repeat what you did without changing that much. But so let's go to protons first. So you can really just switch the modality here to protons. It will reset the status. It will still show the photon dose. It will reset the status, so the optimization will be inactive because you're now working with a different modality for which you don't have the dose, right? Calculated it for photons. And you could, in principle, now just go through with everything again, click these two buttons and get a new plan. But you don't want to work for protons with 5 photon-like gantry angles. Protons need less gantry angles. So that's one of the advantages as well. Like, we do not need to superimpose 5, 7, 9, or 12 beams anymore. You can, but you do not need to. So let's check out what would happen with 2 gantry angles, for example. I like to choose, you can choose different gantry angles. I like to choose 0 is nice. And maybe let's do 220 or something like this. And then you make sure that you have the same number of angles in both fields. MATRAT is not very automated here. And maybe I want to point before we start, or we can hit the dose calculation now for the protons again. I want to point you towards something while the dose calculation is running. Now we have suddenly this type of optimization field active. Okay. And this type of optimization field means actually what biological model am I using? So for protons, the only ones, even if it shows more here, the only ones working are none. So then you would optimize physical dose or constant RBE, which will automatically multiply the RBE with 1.1. Okay, so this is automatically selected. We need to take care. I shouldn't have clicked this because now I need to recalculate the dose. That's a stupid bug / feature. Usually it always resets when you change plan parameters for kind of consistency reasons. Yeah, but for protons, we automatically assume a constant RBE here of 1.1. Because protons are slightly more effective in biological damage than photons with the same dose. Okay. So, and after this, so without much changes, only to the gantry angles and the automatic change here, you can calculate those and optimize those. And now the optimizer will run. It will probably run a little bit longer. So why will it run longer? I don't know. Maybe it also runs shorter, but usually the optimization, it's kind of a rule of thumb. A proton optimization is per iteration faster because the matrix is even more sparse. So you have less dose entries of a single proton spot because the dose is limited by the Bragg peak. There is no exit dose. But you usually also have, since you have modulation in 3 dimensions, right? You have also energy levels, which you didn't have in photons. So you will also have more variables and then usually longer convergence time in terms of iterations. So you see this is running now, and yeah, took a little bit more iterations, and now you see the nice proton plan. So that's, I think, the main thing or important thing about MATRAD is that it, let's say, lets you switch between the modalities very intuitively. For the courses, that's really nice because you don't have to relearn, right? So you just switch the modality and let students create a new plan. And it's also very nice if you want to do some proton therapy research or ion therapy research and just want to quickly compute a reference plan with photons or something like this. So as you see, the proton plan also looks compared to our photon plan much nicer. It has a very nice coverage and very low entrance dose. So you could again save this. So here, for example, with the save to GUI button, you could name it that proton 2 because of 2 beams. I always use nomenclature like that, and you still see. So what you see now is that actually you are no longer looking by default at physical dose, but at RBE weighted dose. So that's important. You are now thinking in biologically weighted dose in a sense. So you want to always think about dose as something that induces biological damage. So that's why automatically MATRAD now chooses RBE weighted dose. Okay. And what you see is that also your old plans are still safe. So the physical dose photon 5 is still there for reference. So you could check it out like this, right? And like switch back. You can also check out the individual beams, right? Like this. And like this, you see they are both modulated, and only when superimposing both, they create a conformal dose in the target. Of course, you can again create a screenshot. So I will just save it now, probably replace what I've done before. I don't need to do any screenshots anymore. And you can show the dose volume histogram again. And this dose volume histogram will be for this patient from like a sparing perspective quite impressive. So compared to the photons, basically there's almost no dose to any organ at risk. And there's only dose to the liver, basically, where the plants go through, and a little bit to the heart, like especially large doses in the gradient region, but the mean doses are very low to the organs at risk. So that's kind of also what you intend to do with protons, right? You want to spare organs at risk. It's not about covering the tumor better. It's not about conformity that much. It's about sparing organs at risk. Yeah, and then you can save this as well to have the data for the proton plan. And last but not least, since we are in the heavy ion course, we now start to irradiate with lead. No, that's the real heavy ions for a particle physicist, right? A lead ion or something like this, but not what the particle therapy community thinks is a heavy ion, namely carbon ions. So carbon ions are probably more light ions, but that's kind of like going beyond protons is actually already very heavy for the particle therapy community. I think, yeah, oxygen is also interesting, but yeah, that's not something that you usually call heavy, right? But yeah, let's just switch now. We can actually keep the beams to the carbon ions. So we really just switch here from protons to carbon ions, and we actually can keep all the planning information. You see that Madrot did one more switch, and it now switched to type of optimization LEM4 underscore RBE weighted dose. Because now we get into troubles with biology. So with protons, also, although it isn't entirely true, I don't know if we already had lectures about variable RBE in protons and so on, but the damage that that ions do biologically is quite dependent on multiple factors that in particle dose deposition vary with depth. So one of these factors, for example, is linear energy transfer, which changes in depth. There are other factors that are interesting, like ionization clustering, which is also related to LET, or radiation quality, linear energy, whatsoever. So there's a lot of factors that could be interesting for biology, but they all change with depth. So now our biology is not only dependent on the tissue and the tissue's radiation response, in a sense, which is usually encoded in alpha beta values in the linear quadratic model, but it's also dependent on the depth. So carbon ion beam will get more and more effective with depth. And this is encoded in biological models. Here, for example, we use the LEM4 model. There's also the modified microdosimetric kinetic model, or yeah, I don't know. There's many models for protons. There are other only LET dependent models and so on. So this is quite a large research field. Yeah, that's so Madrot will try to factor this in automatically, and then for now we can just quickly run this dose calculation again. So we repeat the same steps as before. So nothing changed in the workflow. We are still calculating a dose and then calculating a treatment plan. So yeah, I think that's what we're gonna do now. We're doing the carbon plan, we're calculating the dose and optimizing it. And then I want to show you one or two more things that happened behind in the code for the carbon plan. And I think then we have some time for you to see if you still need something for the exercise, if you want to do a different patient, and to have some discussion. And then I think Jota has some material left, right?
Yes, I have a small presentation. Actually, Niklas, maybe I should go to the presentation so that we are done with that, and then use the rest of the time, and we leave like 15 minutes at the end, 10 minutes to Albana.
Yeah,
so
okay,
that
yes,
people
then
have more time to ask questions and
yeah, then let me quickly finish this plan.
Yes,
and
of course.
Mass reminder of the discussion.
Of
Okay,
course.
so now we basically switch to carbon. We calculated the dose. So this took a little bit longer than for protons. So why could this be? First of all, carbons have a fragmentation tail, so more dose. But on the other hand, they scatter less, so there's less dose to compute. So the main reason why this took longer is actually biology. And if you look into Madrot itself, the Dij, particularly here, has become more complicated. It has now a physical dose, which is the physical dose, and it has pre-computed matrices for the tissue sensitivity, like the alpha times dose and square root beta times dose. That are the terms directly in the linear quadratic model. And since they depend on depth now, they need to be pre-computed as well, at least for our way of optimizing RBE weighted dose for carbons. You could also do this by storing the complete particle spectrum, right? To have like all the spectrum, like the matrices for each ion, and then have RBE tables live computing the RV weighted dose. So there's multiple ways to do this. We use this approach. So there's a lot more data now handled in the background. It's a little bit more heavy on the computational side. And we can click just optimize. So it's really always the same workflow. Set the modality, choose the angles. We just chose the same angles. Click dose influence matrix calculation. Click optimization. And you can modify, of course, your optimization problem as well, just changing objectives, but that's something that we don't do for now or today, because the time is a little bit limited. So good. So you see also this optimization now takes quite longer compared to the proton optimization. So while this is running, maybe let's discuss a little bit, because we really rarely changed any parameters. But if you had all these lectures, you know about physics a little bit now and about planning. So what would be a parameter that we could consider changing for carbon ions, particularly considering that they scatter less? Someone an idea? So what might make sense to adapt when you have quite broadly scattered protons, like protons have quite a strong scattering envelope, and then you go to carbon ions. What might be a sensible thing to change here as a parameter? We will see it probably in the result as well. Yeah, Matthias has an idea.
I think the SSD would be quite a point. So the difference would be in the lateral fall off mostly, and we can change it by changing the SSD.
So if you change the SSD, you get so there it kind of depends, right, on the beam optics, how your beam behaves until the surface, right? If you have a beam that is quite divergent, then okay. So if you have a beam that is quite divergent or convergent, then changing the SSD would change a lot of the beam width when entering the surface. So that's okay. It depends on your beam optic on how you can use this. But what would be maybe sensible is how far from each other you displace the spots. So changing the beam optics, so to get broader spots, like broader break peaks initially, which you probably don't want because you may want to utilize the very sharp fall off to create conformal dose distributions. So you might, for example, be intrigued to not use a 5 millimeter displacement here between spots, but maybe use a 3 millimeter or even 2 millimeter displacement. Yeah, the plan is still optimizing. Now it is done on my computer. And what do we see? Actually, we see much less RBE weighted entrance dose here. So let's say the differential effect is much larger. So we have very low entrance dose. It's still very high target coverage. And of course, we have the tails. So now we suddenly have a fragmentation tail shooting partly through the heart. So that's something to definitely consider as well when planning with carbon ions. What do we have as a question? Yes. Coyote should please mute the microphone if possible. Or maybe a host can mute. So yes, so what you see now is that there is really quite even better sparing of healthy tissue in terms of the dose level because it is so much lower in the entrance channel, but you have the tail. That's something that you have to consider. So so what you again can do, you could now save this plan or store it, like cache it in the system and then do another carbon plan. You can again do a screenshot for your exercises. So basically, if you followed all of this now and saved all the screenshots, you're basically done with as well with the exercise. Or you can kind of also look at a different patient later if you're very interested and do the exercise yourself. Or maybe you had installation troubles and just managed to do it then. So yeah, you can save the screenshot. You can, of course, look at the DVH again, like this, right? So DVH will not look much different than to the protons. There's a little bit more organ dose here due to the fragmentation tail in the heart. Maybe let's make it bigger. So there is a slight difference. Yeah, we are not, so also the target coverage doesn't seem to be very homogeneous. And this is actually really because we took 5 millimeters here, the spacing. You see there's a little bit more inhomogeneity in the target as well. Maybe 4 or 3 millimeters would have led to a better result. There's one thing I really want to show for biology before we go to Jota's presentation. And this is all that we optimize now is RBE weighted dose, and it's not a constant RBE. So we can really check how does the physical dose actually look like. So because it also shows you how important it is to optimize for this RBE weighted dose. So we can really take a look at the physical dose now, not of the photons, and really see that this is quite an inhomogeneous dose here. So maybe let's remove the isolines. So, and can we also remove the contours here? You see that's quite inhomogeneous here. Oh, this doesn't work. Okay, I need to write this down as a bug. But you see this is quite inhomogeneous. And MATLAB unfortunately automatically changed the dose window. So let's maybe go back to RBE weighted dose. So RBE weighted dose is here 1.5 gray. There's something very useful that you can do in MATLAB as well. You can lock these settings, which locks the dose scale as well. And then I can take a look at physical dose again, and then you see that it is really much lower. That's the same color scale now, and we are barely at 0.6 gray here. So really this, you see how important it is for carbon ions to really have this variable RBE dependent on depth in the plan. Otherwise you would create a completely unreasonable overdosing plan. And this is especially dangerous, for example, in this setting. If you would optimize for physical dose, you would have a Bragg peak with a giant RBE stopping right here in the heart, and the fragmentation tail, and will completely overshoot dose into the heart. So RBE weighted dose planning is extremely important for heavier ions. For protons, we are still going with the 1.1, but also there's more and more voices advocating for considering the variable RBE of protons. Okay, so with this, I hope that you got a nice insight on how to work with MATLAB from an interactive perspective, as well as how the data structures look like a little bit in the MATLAB installation here, right? So that you have an idea where to look for what. And just for the ones who want to do research, I want to point out one more thing. The whole workflow of a treatment plan is actually encoded by a script in the file matrat.m. So if you open this, you really see, I don't want to open it as a live script. You really see that all of these steps that we just did are kind of encoded here, and it shows you how to set the parameters by script. It really shows you step by step, and it shows you how to call the most important function as well. How to create each individual of these variables. The STF, the CT and CST are loaded, the PLN is set above. Then how you create the DIJ by calling the dose calculation, and you create the result structure by calling fluence optimization. And you see that many of MATLAB's functions, the like let's say top level functions, always accept these basic structures as input. So they are always your starting point to get through the workflow. So this really goes until here calculating DVHs and quality indicators. So that's a very good starting point to learn scripting with Matrat. And the second very good starting point is the examples. So there's examples on how to create a phantom, like for example, a spherical phantom, how to do photon planning, how to do photon Monte Carlo planning, how to do proton planning. I think in this example, you also have the proton Monte Carlo MC square interface and how to do carbon planning. And this is all scripts. So it's really good if you want to do research to start with these scripts. Okay. So that's it from my side. There is a question which for the assignment, do we have to hand in the dose slices and DVH plots only? I don't know how big the exercises should be. So I think, do they have to write a full protocol, or is it just okay to have the dose slices and DVH slices? I don't hear you, Jota.
Yeah, it's fine. Yeah.
Those slices and DVHs. Yes. So it's basically just to show that you do it, that you have these on, that you did these plans in some way. I think if for those who do really not manage to do anything because the installation will just not work, it would probably also be okay to write a page, right?
Yes, but I hope we will be able to help them with the installation. Yeah, I mean, we are among adults and people that they care for their education. I mean, we will give the certificates of attendance and there has to be some criteria, but I assume people want anyhow to learn, and so it's up to you. If you want to do more, of course you do more, and if you have questions, we're here to answer the questions. Okay, good. So Angelica, if you can share my presentation and go to slide 4. And at the meantime, Nicholas, one thing that you pointed out, and we have to be also careful with the particle therapy master classes, is this fragmentation tail of carbon ions that usually people come to the conclusion that this is not a good plan compared to proton. And this locking the settings that the reading on the dose is when it is read is not always the same value. No, I mean, this is something that we have to point out. Okay, so back to the presentation, so that we are done with that. So now that you have become familiar with Matrat, let's see how we can use it within the framework of masterclasses as means of education and capacity building. So on the right side, you see the virtual therapy center created within the Enlight network. But as you have heard, we are working on the design of new facilities to fill the gap in the Southeast Europe and in the Baltic countries. So we really need people that become experts on this, but also for the current and future therapy centers all over Europe. So in a nutshell, the idea of the masterclass is to combine different pedagogical elements, including hands-on, that facilitate learning. So we try to give a whole idea, starting from the ion sources to the beam delivery and treatment planning. And in the simplest and original form, the particle therapy masterclass is addressing high school students at the last classes of the school before they start their university studies, using, of course, as we said, a simplified version of Matrat. And needless to say, one can use it in many different ways for educational and research purposes. And obviously, by elevating the level, one can address university students and researchers at different levels. In the next slide, we have a summary, a historic summary, developing the particle therapy masterclass in 2019. We first tested it locally at GSI, and then we did another pilot involving 3 institutes that contributed to its development, GSI, DKFZ, and CERN. Each one of them performed it locally and independently, just before the COVID pandemic, where we could do it in person. And then we all joined a common video conference to discuss the results with experts. And based on the feedback we got and the improvements we did, the particle therapy masterclass was approved and included in the international masterclass program that runs since several years already. And you may have heard of that, that is based on particle physics data. So as an example of different ways to use it, you see the picture of the CERN Open Days, where we participated in the standard mandate organized actually. In the next slide, we see in a nutshell, during the typical agenda of this particle therapy masterclass that are a full day event. So we wish to give to students the opportunity to become scientists for a day. The program runs every year from mid-February to mid-April, and 3 to 5 institutes around the world every day invite students to participate either in person at the institute or online, adapting to the pandemic. So the idea is that it includes a multitude of pedagogical elements that facilitate learning, lectures in the morning, starting with videos while participants are connecting to give a visual impression and help them relate what they would listen later during the lectures, visits to a laboratory or an experiment, or virtual visits during the pandemic. And after lunch, the highlight is the hands-on experience with real data. And then to prepare a presentation with the results for discussion in a common video conference with all other institutes of that day and moderators. So in the next slide, you see a typical agenda from institutes in Italy, actually. And later, my colleague from GSI, Albana Topi, will tell you how she organized it for several institutes, including her home institute back in Albania, from the point of view of the local organizer. Practically, the local organizer has to contact a school, the teachers, and organize a date that the student will be available, or alternatively, do it on a Saturday and send announcements via social media. Then one has to find speakers for the morning lectures and assistants for the hands-on sessions that are done locally. Then connect to the virtual visits and common video conference that is organized by us, the core team. And the video conference usually finishes with a funny quiz that Albana will show you later. So in the next slide, you see some of the material that is available in the web pages. And the material is available in several languages, including recordings. And you can find plenty of presentations via the Indigo page of the institute that participated already. In the next slide, there is some more information, and I would really encourage you to take a look at the videos and play with this interactive hadron therapy facility like a game that is also provided within the Enlight network. Also, you can look at the presentations with recordings in conference proceedings that give more details. So in the next slide, just an example of bringing this to a higher level, inspired by this project and its format, we organized the first heavy ion, the first HITR Plus school in a similar way, of course, every day for a whole week. And obviously the level was higher. So the school included lectures in the morning, starting with overview talks to give the necessary panorama and then going to details, hands-on in the afternoon, student sessions with presentations and discussions of the results with experts from different institutes, virtual visits to existing therapy centers guided by their experts, and every day started with videos while participants were connecting. Every day ended with social events to provide opportunity for networking and entertainment. And of course, the last day included flash talks, future developments attended with a careers fair in the evening. So in the next slide, like a summary, in general, the Heavy Ion Therapy Masterclass School addressing university students and the Particle Therapy Masterclass addressing high school students aim at introducing them to the multidisciplinary facets of the heavy ion therapy. and making them aware of the different interesting career paths in emerging fields, for example, accelerator physics, medical physics, biophysics, and many more, where actually often there is lack of specialized personnel. And also they both provide information about upcoming modern techniques for cancer tumor therapy and new research avenues that are actually expanding in Europe and worldwide, as you have seen during the presentations this week. And where clearly the development of technology and the expertise of research laboratories is crucial, because this is another objective, to show to the public the effect of fundamental research in everyday life. And of course, we hope that many of the participants of the school will become tutors for the next year's particle therapy masterclass, and hence also the title Train the Trainer. So in the next slide, just to point out that participants really like very much the virtual visits and video conferences. And for example, during the video conference with experts from Knau Therapy Center in Italy or Medostron in Austria, they have the chance to ask questions and enjoy these virtual visits of the accelerator complex via webcam and therapy rooms. This is complemented usually by a virtual visit at the GSI historic treatment room, and they are always surprised to learn that some 500 patients, 450 actually, were treated there with 95% success before the carbon therapy was introduced to the clinics of Heidelberg and Marburg in Germany. And this is a very clear example going from physics to clinics, from the research laboratory to the treatment, to the therapy. And I have to say that we were honored this year to have in one of the common video conferences moderator Ugo Amaldi, who gave an introductory presentation as a pioneer and the father of the Knau Therapy Center. In the next slide, just that you see visually the participation to the 2021 particle therapy masterclass session was overwhelming, reaching actually more than 1,500 students from 20 countries through 37 institutes that participated in 6 full-day sessions that we opened. In the next slide, we see a similar participation in the 2022 season, with participation of countries from Latin America up to India. And as I said, they all provided material in their own languages, publicly available, that anybody can use for future events. For me, this shows the interest of the students, but also the motivation of the tutors. It is all voluntary work, but also the potential impact of such activities. And I have to say that we always provide training sessions that we plan, but also training sessions upon request. In the next slide, as an example, we have, since I'm Greek, I chose Greece as an example. We ran them on Saturdays, and it really became a national event, thanks to the publicity via the Library of Veria, my hometown, to their extended networks and national press. So actually we had sessions with over 150 participants from all regions in Greece, even remote islands. And this is something positive we have learned during the COVID pandemic. So in the next slide, I just summarize why I think this is important. So we wish to use the particle therapy masterclass as a tool to support capacity building and to make aware students, but also their environment, families and friends, about particle therapy. And in general, the aim and expectation is to attract school children to STEM studies at early stages when they decide about their future studies and career, and cultivate confidence through the hands-on, giving the feeling I can do it. And in fact, the master thesis study that I co-supervised has shown that the students actually learn based on analysis of surveys, and actually the defense is next week. In particular, we support female students. We celebrate the 11th of February and 8th of March Women's Day with special particle therapy masterclass sessions where the tutors are female, but the classes are mixed. And we try to handle prejudices. For example, this is a subject of the master's and then a PhD thesis of one of my students from Mexico. We want actually to create groups of university assistant tutors that learn themselves better in order to teach the high school students. We demonstrate a return to society from fundamental research, enhance awareness of broader public, and we hope to prepare the future generations aware of the importance of fundamental research and its applications, spanning from politicians to an evidence-based decision-making society. That I think is quite important. So in the next slide, as I said before, the particle therapy masterclass is integrated within the international masterclass program that is the flagship project of the International Particle Physics Outreach Group. And this is reaching about 15,000 high school students every year from 60 countries around the world through about 255 institutes that participate every year, and offers masterclass packages of the LICI experiments with several additions lately, one of them the particle therapy masterclass. And of course, the material can be used for local events, for teacher training, or whatever one can think. Actually, somebody said that based on the material that exists for the particle therapy masterclass, they're going to create a master's program at their university. So in the next slide, just to contrast, being myself a heavy ion physicist working at the ALICE experiment, involved recently in heavy ion therapy, I first developed the ALICE masterclasses highlighting the role of heavy ions for fundamental research at high energies, and recently the new particle therapy masterclass highlighting the use of ions for cancer therapy at lower energies. And this clearly demonstrates benefits for society of fundamental research, and several institutes actually they do it back to back. So here, as Niklas said, we also see what is heavy ions for heavy ion physicists and what is heavy ions for therapy. So, and here let me take the opportunity to elaborate on the question that was asked by a theorist this morning on the details of the equations. Going back to the presentation of João Seco, or coming to this particle therapy masterclasses for high school students, one has always to balance, one can explain with words or write next to it the equation. But what we tell the students, we write equations, not in full detail, but we don't want to give them the impression that in 3 hours they can do miracles in the work of a PhD student. So we tell them, and we don't go to the explanation, we just state that there is some complications behind it, and they will learn when they go to the university. So needless to say that one can use it in many different ways for educational and research purposes, and the level is to be tuned according to the audience. So in the next slide, I will finish with my usual acknowledgements, because this is not one person work. Special thanks go, of course, to Manjit that initiated me and guided me to this new field and put me in contact with many of her students. And one click more. Yes, special thanks go to the core team of 2022 that include students from Thessaloniki, Sarajevo, Montenegro, Albania, but also from Mexico. In the next slide, as an example, I show a picture from Sarajevo where we were supported by a private sponsor, and we run now both the ALICE and the particle therapy masterclass with about 150 students each year for each one of them. And this was actually the beginning of many common projects that is the topic of another presentation. So the next slide, I will conclude that with such projects, we try to support capacity building, and we hope to collaborate in the future with many of you. So in the next slide, thank you very much for your attention, and don't hesitate to contact us for any further details. And once more, I would like to thank all my colleagues for participating today and in the overall project. Thank you. So now I think we can go back to playing with Matrad. And of course, if you have any questions, I will be happy to answer. Niklas, back to you, I think.
Back to me. Yes, so I don't have any more planning now planned?
Yes, but you have the exercises that the students have to do, right?
Yes, so the exercise the student have to do
That's why I
was,
try to finish fast so that they
yeah.
have more time to play.
So
Just give me 15 minutes for Albana to explain from her side at the end as a local organizer and do the quiz.
okay, so if Albana needs 15 minutes, then we are already at the end, right? So
No, we have till 1 more hour. 1
Yes,
hour and 15
yes.
minutes.
Yep.
let
Right.
me check. I am. There's the whole now I get it.
Yes,
Yes.
I have the presentation, but I have done it already. So the whole
Yes,
session
yes,
finishes
yes.
till 6. So now we can go till the end
Yes,
minus
I thought
15 minutes.
I'm
Yeah,
on
yeah.
until 5, so
Yeah.
but okay. So for my side, I don't want to do any more planning right now. Like basically, you just following me. Also, since I seem to skip out of, I mean, in the last hour it has been quite good, but I seem to skip out all the time. So first of all, regarding the exercise, I will share this again now because I think, Jutta, I sent you the PDF, right? Was it attached?
By mail you sent me?
Yeah.
Let me check
And
to see.
because then you
I
can
will upload it. Okay.
upload to the Indico session, and I will share it for now again. And there have been some questions as well. So let me quickly need to set this up again. Where's now? So this here, this is the exercise. So basically what you see, if you followed everything what I did, you kind of have the exercise already done. So you can either kind of clean everything up or look for a different phantom that you're interested in doing. So maybe load the prostate and choose some beam angles, or load the phantom to just see it in an ideal condition, how it behaves. But that's actually what you should do. So we just want to have the 3 modalities side by side on one of these phantoms. So you start with a multi-beam photon plan. So I chose 5 beams, but you could also go for 9 beams if you have a powerful computer at your hands. And then you create a proton plan and a carbon ion plan. So that's actually what I just want you to give you the time to work on this a little bit. So, and while you're working on this, I will be available, let's say, to answer questions, or if you are interested in, basically, I think it's also a good time if you have any questions that you are interesting about how to use Madrat in a educational environment or in a research environment. Maybe I can give you examples of how it was used and so on. So just feel free to use the next minutes. So I think I can be available until 15 minutes after 5. So just use the time to work on the exercise, ask questions, and yes. So
the presentation is in Indigo. And actually, Nicholas, many times you say that if somebody is interested in collaborating with you, you are open to collaborations also, if people want to develop things in collaboration with you.
Yes. So if you have a research project, and so maybe that's just something to talk about a little bit. So if you have a research project, so a current example was like an example that was a PT-Cog, ended up in a PT-Cog presentation a few days ago, was like a flash optimization. So basically we started with Joao Sicco and students of him here to build a average dose rate optimization within MATRAD. And then another group approached us if they could do average dose rate and LET optimization. And so that's then we said, okay, we can help out and can point towards the right direction and so on, how to implement it, what needs to be changed in MATRAD. And there we really like to help. So if there's like, so when you interact with us, the best way is like, if you really want to collaborate in a sense, then it's good to write an email and then we can figure something out. We have a little bit more manpower now on MATRAD than we had before. So there's more developing going on. The best thing, of course, if you really want to contribute, what we usually so what we usually like to do is like really interactively. So maybe there's a student and then help with specific details, maybe sometimes have a meeting. What we don't do in a sense is contract work. So if you like, that's always what I call it as a joke, but what we are not up to is basically someone just asking, can you implement this for me? And that's not how this works. If it is on our radar, then basically we will say this will be implemented soon. If many people ask for it, then that gets more probable, but we don't just implement stuff. But if you are willing to code a little bit or need some help with it, need pointers in the right direction, we are certainly willing to help. Yeah, best thing is always if you contribute. If you want to be a contributor, just also write on GitHub, say, hey, I want to work on something, or I have something implemented. I have done this for my research project and I really want to be available to the rest of the community. Then there we are also, of course, happy to help with and give some indications or some indicators on how to design the code or whatsoever. Good. We have some questions. When I do the optimization steps, sometimes I get less iterations than what was shown on your screen. Yes, so so I can quickly explain how the optimization in MATRAD decides on how many iterations to be done. So basically there's a stopping criterion in the optimizer. So the function that we optimize has a minimum, but we don't know what the minimum is, right? So because we have the sum of all these dose deviations, we don't really know what the optimal value is. So we don't know that the minimum will be 0 and we just have to find it and have to find the right variables. We don't know what the value is. So the stopping criterion to decide that we are close to a minimum is just to check the last few iterations and see how strongly the value of the function changes. And if the value changes not enough, then it will stop. So, and this can be different. So there's different things that can influence when this will happen. So of course, the optimization settings. So if you have different penalty values and different dose reference values, this might change how many iterations you have. The reasons for this is that the solution might become less degenerate, for example. So less degenerate means it is more clear what the trade-off means. So for example, if you take the liver patient and just set a target optimization objective and the skin or like rest of the tissue optimization objective, there is like a myriad number of solutions that can find you can distribute those in so many different ways to get close to an optimal point that you might end up in like kind of a plateau region quite quickly and the optimizer will just stop. or you might basically have a very much more difficult trade-off to find, and then it might take longer. But it's not easy to say how long it will take. Let's say it's optimization convergence, but it shouldn't be runtime. So the number of iterations shouldn't be related to how powerful your computer is, because the numerical side is the same on every computer, right? It's just computing the same things, but it takes longer. Not in terms of how many iterations, but per iteration. In each iteration, the optimizer needs to evaluate the dose. So it multiplies the dose matrix with the current fluids. Then it runs all objectives. Then it computes all objectives, sums them up. Then it computes the gradients of the objective. Then it passes it on to the optimization package, which then like solves the inner system of the KKT conditions and so on. And this is numerically, this is kind of equivalent between computers of every power, but it will take longer to do all these computations, but the number of iterations will not change. The steps will be the same. There can be some differences due to parallelization. If it's that different sums, like slightly numerical deviations that affect the step, but usually it's really just what do I set as optimization objective, what modality do I use that changes the number of iterations. So this was a long answer, but I like to talk about optimization.
Any other question? Take the opportunity that now that, yeah, Matthias.
Yes, I would like to know, you said that you are about to release a new update of MATRAT, and
about to, maybe. So yeah, the problem is the last release is quite a long time ago, but we had the problem that there were so many divergent developments that we're really working towards a giant release. We hope to do it in autumn or something like this.
okay, and yeah, then the next question would be when, how much earlier do you normally communicate that there will be an update or something?
So I would say our communication strategy was not the best with the last updates. So with the next release, we really want to establish a somewhat more regular schedule. So to know that there will always be a release in autumn, for example, or something like this. And so in the future, we will probably communicate a new release via our mailing list. I don't know if you know about the mailing list. There is a mailing list you can kind of sign up with, which is a document that I have and that I will send out. Sometimes I will send out reminders or like announcements. So in the future, we will communicate it probably like 3 months before, or when releasing a first beta/release candidate, then we will communicate it and then do some testing, and then it will be probably 2 months or something like this until the release is done. So this is, I think, the timeline, and in the future we will probably go for something like have a released at least once a year towards autumn and patches in between.
Perfect, thank you. And then one remark, I'm currently working on MATRAT, and I'm pretty sure I will contact you if it's possible, because I have still some issues.
Mm-hmm.
And yeah, I think it would be really, I would really appreciate it if I could get some tips. Yeah,
good. Really just contact us. So you can always write me an email. Sometimes I will forward it to a student or a postdoc if they are working on the topic more closely. So because in my research group, most of the people are somehow working with it to generate plans, or because they do some direct research on it. But yeah, just write an email or write something on GitHub. So if you identify an issue or something is not clear at all, write an issue on GitHub. We are really willing to help if you explain your issue well enough so that we can help. And yeah, so yeah, so really no hesitation in contacting us there.
Thank you very much.
If there are no other questions to the experts, then maybe I suggest to play with Matrad and try this workflow that Niklas suggested, having different data or different, yeah, I mean, maybe it was too fast. I see the questions how to submit the exercises. In my presentation, in the first slides, I have maybe the second or third slide, a box, a blue box, where it is marked that you can submit your exercises by email, and the email addresses of Niklas and Manjit. So they will go through them and also see the participation of different participants in order to grant the certificates of attendance. So,
Sorry, and we have to,
yes.
to do the 3 sessions of exercises that are in the Indico page.
So
No, in the
yeah, that's a little bit confusing.
no.
So there are 3 workflows, and these workflows are only uploaded as a reference for what you can do as an educational course. So these 3 workflows, the Tuesday, Wednesday, Thursday stuff, that's really just some reference stuff. If you want to give a course, that might be some good material. The exercise.
I cannot hear you.
So
yeah, let me repeat what
on
Nicholas said. So in his slides, in his presentation, there are some suggested exercises that are the ones that we ask you to do and submit. As I said also in my presentation, last year we had 3 days hands-on, and we used these workflows that are in Indigo that are there for reference for you if you wish to use them for any classes that you may want to perform or for yourselves to train. And as I have described also in the Train the Trainer, Indigo, in the tab, I have also put the links, direct links to these workflows and the corresponding recordings. So together with the doc files that you have also uploaded in Indigo, you have the recordings. So you can practice for yourselves and you can use it for any classes that you may want to set up, okay? But for the certificate of attendance is enough to deliver the exercises that are written in the slides of Niklas. Is it clear?
Yes, thank you very much.
Okay, any other questions from anybody else regarding these practical issues?
I think there was like one question, just to say this again. That was, I want to be sure that we must submit 3 dose slices and 3 DVH. Yes, I think that's good to submit, like the 3 dose slides of photons, like 1 photon, 1 proton, 1 carbon ion for the case you select, and the corresponding dose volume histograms. So the dose volume histogram for the dose of photons, which will be in physical dose, and the RBE weighted dose histograms of protons and carbon ions. Matrad will automatically select the right dose, so don't worry about this. Yeah, is there a deadline to the exercise? 11th of July?
Yes, it's also written on my slides, but I went very fast through that. Okay. Any further questions? It seems not to be the case, right? So then we let you, yeah, there is one more question, but meantime, people can start running the exercises by themselves, like for 15-20 minutes, something like that. If it is okay with you, then we can discuss some of the results that you are going to produce. You can share your screen and show us the result. Albana will be here to comment on that, simulating somehow the common video conference of the discussion with the experts. There are, okay, Sarnai, please go ahead.
Hi, thank you for all the help and the very good talks. I just wanted to ask how soon the lecture will be uploaded onto YouTube, because I saw that the instructions are very nice in Indico. However, I'm someone that doesn't have a lot of experience with this. So for me, I would like to also just visually confirm that I'm doing the right thing at certain steps. And I know that the lectures, there's an intention to put it on YouTube. So will it be submitted or put onto YouTube before the submission date? Or do we just hope that we're doing the right thing for those of us who aren't really experienced with this particular section of research?
So we can have it on YouTube by the end of today.
Oh, perfect. Thank you.
No worries.
Yes, there is one more question by Matthias. Please go ahead.
Yes, again, regarding the updates you're about to release sometime. So can we see somewhere what are you going to implement in the new releases? Because I'm also using GitHub, and I'm seeing the different forks and seeing the different developments, but it's not quite. So I'm not quite sure which will be the implemented, which of the updates and what features and.
So yeah, it's a little bit hidden into some. There's like this project tab, and there is one project which is kind of called update blah 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 branch for next major release Matra 3, and there you basically see what will be there if you find it. There's like this project tabs on GitHub, and there's like one project. The projects they're not well managed. They are basically I mean the one interesting for you should be the second one, update devvar RBE rob opt for next major release.
Oh, okay, perfect. Yeah, it's the first time I really saw this one. I'm not so into GitHub. I just started because of Matrat, and so I haven't seen this before, but this really helps. Thank you very much.
Yes.
Niklas, there is a question in the chat.
It's about not seeing structures. Let me check. Okay, I will check if there's some. Someone is saying that loading, is this the standalone version or Matrat from MATLAB?
Alexandra, would you like to share your screen to show the problem and give some more details? You can unmute and describe your problem actually.
Yeah, hello, can you hear me?
Yes.
Okay, then just a second. Let me open the file and then maybe I can show you what the problem was. Okay, and then maybe like this. Okay, can you see it?
Yes.
Okay, so when I load the prostate metadata, I just can't see this here basically with the structures.
Okay, yeah, I'm currently trying to reproduce it.
So for the head and neck, it's visible, everything is fine. It's just for the prostate, but that's fine. I can just look on the other file.
Yeah. So what might help just is maybe there's something not reset. So what might help is to just close. So are you using the standalone?
Yes.
Yeah, I see it now. So what might help is just to close and restart. I think
Okay.
there is something not correctly managed maybe when switching, but I don't know what it is.
Okay, I'll give it a try. Thank you.
Does anybody else has a similar problem actually?
So because when I start a clean, I just started it up new and I see the structures. So maybe if you switch from a certain patient to another patient, there might be some bug. It's weird that it affects the prostate, but not the other ones. Yeah, I will be 10 minutes longer for questions on the exercises. Or questions on MATRAT, or questions about optimization, dose calculation. So maybe because the question was earlier, I can just talk about this while you do the exercises. There was one question about the cross sections, which is an interesting question. So which kind of relates to what dose calculation algorithms you use. So I think the gold standard in dose calculation for particles is Monte Carlo. In photons, there's also these radiation transport solvers, which can also be very good in accuracy because they also solve exactly numerically the radiation transport equation. But the gold standard is Monte Carlo, and when you simulate Monte Carlo, of course, you need the data tables for certain cross sections. Many Monte Carlo algorithms in particle therapy are a little bit simplified. So if you want to get fast, you often simplify certain stuff. So find good approximation, like find more efficient approximations for multiple Coulomb scattering, and so on. So depending on the Monte Carlo algorithm, you would use sometimes also different details of input data. So MATRAT interfaces, like what's included in MATRAT, because they are also open source, or is for protons, the MC square Monte Carlo, which is a very optimized proton Monte Carlo on the CPU. And there's some data. So if you look into the MC square folder, there you can find some data, but I have to check again what data Monte Carlo, what data MC square uses. They definitely have stopping power tables, but probably that is simplified to just being the total stopping power. So both electromagnetic in a sense of both Coulomb and nuclear. So it's not clear how well this is separated. So MATRAT also interfaces, but they're the TOPAZ, but there you need to obtain the TOPAZ license yourself. It's also free, but you need to specifically apply for it. And this uses, for example, the Geon 4 tables and physics lists that are available there. MATRAT itself, so just for the reason that you can be fast enough on your, let's say, private computer to run a dose calculation, because that's also not trivial, and that what was it also initially the goal a little bit, to be efficient enough to run on your private computer. It uses so-called deterministic pencil beam algorithms. So what this means is that MATRAT has a database, has databases of tabulated depth dose curves and scattering kernels within water. And it will use the method to compute the water equivalent path length given a relative stopping power conversion of the CT to kind of scale these dose cubes to the patient. It's not the most accurate dose calculation algorithm, and it will fail quite drastically in lung, for example, or in heterogeneous media. but it is quite acceptable in the head. And when you calculate doses for treatment planning, using Monte Carlo is also challenging. For protons, where you have like, you can streamline Monte Carlo very well and kind of optimize and approximate certain contributions, certain physics very nicely. There, the Monte Carlo algorithms are also going towards use in treatment planning. But the problem in treatment planning is with Monte Carlo, that you need to compute a statistically sound estimate of the dose for each of the individual pencil beams, because you don't know how to distribute them yet. So before treatment planning, you need to kind of already, so you do not know how much weight you would put on an individual beamlet, right? An individual Bragg peak that is somewhere in the target, you don't know yet how much dose this should give of all the beamlets. So you need to compute an estimate for all of these beamlets, which can be 60,000. And you can then think, what does it mean to have 60,000 statistically sound Monte Carlo simulations in the patient? And then you optimize, and after the optimization, it is clear, right, what, or you have a decision on the fluence for each individual beamlet contribution, and then you can make, let's say, a global forward dose calculation with this initial fluence, needing much less particles in total, or much less histories in total. So for planning, it's often common to use simplified approximated algorithms like a pencil beam algorithm. And that's what we use in MATLAB, but you can also use Monte Carlo, and then you will also have access, or you will need these tables. So that's maybe just these cross-section tables and stopping power tables and whatsoever. So that's kind of what you should always take care of. Or like consider that the dose calculation algorithm is a little bit simplified for you to be, for you to be able to compute this on your home computer. Because when you look at the really, really fast Monte Carlo dose calculation algorithms, they usually use 2 high-end GPUs and high-end CPUs. If you look what, I don't know, if you buy a treatment planning system from a commercial vendor, you get a workstation with it that has lots of computing power to be able to run these things in, let's say, less time at the minute scale or something like this with Monte Carlo, for example. Or there's also ways to make the deterministic pencil beam dose calculation better. You can use subsampling and so on, but that's a little bit too much detail.
Okay, thank you, Nicholas. It's exactly 5:15, so you are off the hook.
Oh, are there any more questions, any issues with doing the exercises? Or is everybody just moving along and creating pictures?
I don't seem to have questions.
Yeah. So then, yeah, I need to leave now. So I hope everybody had a little bit of fun, or is having a little bit of fun with the software and creating some pictures for the exercises. I think we are all excited on what plans we will receive. Yes, have a nice remainder of the school.
Thank you very much, Nicholas. Thank you.
Thank you. Thank you very much.
Good.
So now we are ready to see the results. Is any one of you ready to share screen and share your results? To start with photons, maybe? you have not finished yet any of the exercises, maybe we give you another, I don't know, 5-10 minutes to produce a photon plan.
I have a photo.
Okay, great.
Bit bad, but we can show.
Please go ahead and share it. And Albana Top is here. She can comment. Albana, maybe you want to introduce yourself to everybody. Thanks for joining us.
Hi everybody, and thank you for being here. And it's a really great pleasure to be part also of this school for this week. And I'm happy to see your presentations and to see what results you got. And I hope you had a great time. Nicholas made a fantastic job in this afternoon explaining all the theoretical parts, being this for a standalone, but also for the program when it's used also with MATLAB, so the development version. I'm Albana Topi and I'm a postdoc at GSI. And I have done in the last 2 years these master classes. So basically Jota approached me and asked if I could organize these master classes in my mother tongue, because I come originally from Albania. So I contacted some people, some professors in Albania, but also in Kosovo and North Macedonia when we organized these master classes last year, but also this year. And I'm happy to share my experience, but at the moment, maybe we can also comment or see what are the results.
Yes, please go ahead.
No, I thought that when I did the screenshot, also the parameters would appear, but apparently not. Can you hear me?
Yes, we can hear you.
Okay. Well, what I tried to do is just to not irradiate the bladder, so coming from these angles here. But what happened when I did is that I'm actually irradiating the bladder quite a lot and the rectum. So I don't know how you would do this irradiation without compromising so much the organs.
So basically you're asking what would be a better approach to deal with this case. And this is the photon case, right?
The photon case, yeah, because I also did proton and the proton.
Yeah. Well, one option would be also to think about, okay, in which side of the body we want to irradiate and to focus our beams, let's say, in that direction and not in the opposite direction. And using angles that come in such a way that they are not hitting the organs at risk that
so you would
have nearby.
Also, you would not only the gantry, but also the if we rotate the bed, we could.
Yes, that would be, of course, an option, but also, like, first of all, having, like, let's say the angles concentrated on one of the sides where, for example, if you want to irradiate the part that is on the left side and starting maybe with 1 or 2 angles in the beginning and then try.
Because we can change the isocenter, no?
Sorry?
Because we can change the position of the isocenter.
Well, the isocenter, you have given, depending on the version that you have used, I don't know exactly. Because
I use the one from MATLAB because I have MATLAB.
No, you don't change the isocenter. You always have to have this cross.
Right.
And this is, yes. What Albana says is to change the angles. Yeah, to play with the angles, geometrical problem practically.
Okay.
Yeah.
Basically having them in the range, for example, from, I don't know, 250, to maybe 300 to 200, and then see, for example, if you want to irradiate only the left part, and then see what, starting with 1 or 2 angles and trying to optimize or to see what will be the best kind of shot to have a better coverage of the tumor, but sparing the organs at risk. And then you will see that also analyzing those histograms, that the moment that you have you change these angles and you see what is kind of the better option, you'll see also in values, in terms, also in the table, but also in the histograms as well. I don't know if he's.
Yeah.
Thank
you.
Sure.
You had another plan with protons, or it was?
Yeah, I was just doing
Mhm.
this one. Well, it's much better, I think. These two, yeah. And this would be the definition. It's already, it's still not so good, I think. I was just trying to play a bit with the angles and also the organs at risk deviations.
Request to sit on the accelerator panel session at particle accelerators would be. No, this is nothing to do with this. Just sorry.
Manjit, is you, or whom do we hear?
Yeah, it was Manjit for a moment. I think she forgot her.
Yeah.
One.
Not for us. Okay.
No, sorry. I was just looking at a request that came in. Sorry. No.
Yeah, no problem. So somebody else that would like to share the results?
I would like to just make a comment on the last plan. We saw the proton plan. It looked quite good on DVH, but if you look at the angles you were using, the incident angles, you saw that you would irradiate through the table.
Through the?
Through the table, the patient table. And this is something you would never do in the clinical setup. That you would.
Thank you. You can see I'm not in the clinical. I was so focused on the tumor itself.
That's a classical error, which also happens in the clinics. Like you search for the best angle to irradiate and to spare healthy tissue, and then you make mistakes like irradiating to the patient fixation or the table, like you saw it. That's a classical error, which happens quite often.
Thanks for bringing this up, because it was one of my naive questions as a physicist doing fixed target experiments. That was my first question. How come you use the 360-degree gantry practically, that in a way you don't want to go through the table, right? Of course, the answer is also that they are made out of carbon fiber, and what you have to avoid is the edges, etc., but in principle, one should avoid going through the table, right? Yes, thanks, Matthias. Very nice comment. Somebody else that you would like to present the results? Particularly if somebody has done carbon already. Is there anybody that managed to do carbon? Takes a little bit more time. So don't be shy. Share your results. No, nobody? Is it that you have not finished? Is it that you have difficulty doing it? What is the problem?
Probably they might need a couple of more minutes to finish and to think how we normally organize the master classes. Also, when we have the one-day event, only the whole day. Is basically within a day having the theory and having the practice, basically the hands-on session in the afternoon, and already for the common video conference, kind of the students have to prepare the slides and show the results within a day. So it's a lot of pressure on the students, but I guess also for you, probably some of you have managed to get some results or some tests and
So I don't see questions, so there shouldn't be problem. So it is a matter of time, possibly.
Or at least if they can, or if you can give us some feedback. So how is the, if you need more time, or Luisa? Yeah.
Yes, can you hear me? Okay, yeah, so I can share my carbon ion plan, but I just did one beam. So yeah, but I can show what I did. So yeah, on the top you can see the dose distribution or the dose slice, and then the DVH. Yeah, I tried to spare the heart, of course, and the spinal cord. Yeah.
Okay, so here you have used one angle only, and of course, in the case of carbon ions, it's not the same as in the case of photons when you use more angles because you want to shoot in different angles in such a way that you can cover the volume of interest. And yeah, this is clear. I don't know, sorry that I wasn't actually in the whole time during the when Nicholas was explaining, probably also showed such examples, or I don't know, Jota, if
yes, he has shown these examples. Yes. Actually, can you you have done this same exercise for photons and protons also?
Yes, I
Yes.
can just scroll up a little bit.
Yes. And maybe you can read the maximum of the scale in each one of yes, so that we know to what the red corresponds, because as we said, it may be different for each one of the plants, right?
Yes, so I don't know if you can read it here, it says 1.6. Yeah, so for the proton plan, or actually for the carbon plan, I changed the angle because of the tail region. So if I had used the same angle as for the proton plan, I had irradiated the heart. So that's why. Yeah. So this is the proton plan, just one beam as well, because of my slow laptop.
So the maximum of the scale for the proton is 1.6, and what was for the carbon?
Sorry, 1.8. Yes. And for the photon plan, sorry, here it is. It's 1.5. Yes, and it's 5 beams. Yeah, maybe not the best solution, but yeah.
Okay.
So you want to look at the dose distribution histograms also? So here it falls quite steeply. This is the photons, right? Yeah.
Yes, it's for the photons.
Yeah. And going further down to the proton and carbon ions.
This is for the protons.
Yeah, where you see less dose already in the organs at risk.
Yes. This one is for the carbon ions.
Okay. Perfect. You have any other comments, Albana?
Well, maybe just a naive question.
Maybe I can add something for the photon plan, and maybe someone else knows it better than me because I'm not a clinician. But as far as I know, in the clinics, you would always try to have an odd number of beams, and you don't want them to oppose each other. So because a photon has a large range and also distal to the tumor deposits a lot of dose, so you don't want a beam coming from that opposite direction. So you're trying to distribute the dose inside the tumor with like overlapping the beams. You get what I'm saying?
Yeah, so basically, not the 0 degrees and 180,
exactly,
for example,
exactly,
for the other one.
Yeah.
Yeah, that's a good point as well. Yeah.
On the other hand, what Niklas has as good example, at least for carbon, is two beams exactly opposed, where you practically don't see the fragmentation tail of the ions, but it is done in such a way so that before and after the dose is below the value that below the constraint that they have defined. So I see a question from Redona. Please go ahead, Redona.
Do you hear me?
Yes, very good.
Okay, I have done all the exams here. I can share it to
Please
see.
go ahead.
So, yes, just 1 minute. Okay, do you see my screen?
It's
Sorry?
coming, not yet.
Slowly.
Has started screen sharing, but we don't see yet.
No, do you see it? No?
No.
Redona, you have to double click.
Okay.
There, that's it.
Yes.
This one. Now, do you see it?
Yes.
Okay, I'm Redona from the North Macedonia. I'm PhD student, and I have shoes for the exercises, the liver case. And the first one was to take, for example, 5 to 9 beams, and I choose to take the 7 beam. Here I have written the gantry angles, and I have the results is these pictures. You can see it. Sorry, the first one was for photon beams.
But
Also,
here, yes, but here,
yes, I have here also and the diagram. Just 1 minute. Here I have the expert dose, I can say, and dose volume histogram for the first exercise. And we can see the values here for maximum and minimum. For example, in the liver here, we have maximum 1,5 gray. And also, we can do the difference between first exercise and second one. Here is, for example, to take 3 beams or 3 gantry angles. I choose to take proton beams. And this was my my results. So just 1 minute here, I think. Yes, this was the results for the second one. And we can see that if we have proton beam, the liver here have the value for 1,5, also the same, I can say. And the third one is to create also one histogram with carbon ions plane, but with 2 angles. And the histogram is here. Also, we can see the values for liver, because was my cases. I choose to take liver cases, and also is 1,5. This was my.
Thank you, Redona. Just to clarify, Niklas used equidistant angles just because it was easier, but you don't need to use equidistant angles. And for example, in the first and the second treatment plan that you have done, you see the beams going straight through the heart, right? And somehow you can manage to have the ankles in such a way that you avoid the heart. Yeah. So as Albana was saying, also concentrate on the left side, concentrate your beams at the left side and avoid both the stem and the liver. But Albana, you are the expert working with the treatment plan, so I should let you comment. Please go ahead.
Well, overall, it was a good presentation, and also comparing all the results, being this in the picture that we see, but also in the numbers. And of course, the comments that you said about the direction that the beams are coming. And this is not from the kind of just in general, when you try to save these images or the dose histogram, try to zoom kind of the page or the window in such a way that you can see them nicely while you have it open before you save it, because then it's just from the aesthetic point of view in general, like advice for everybody, because it takes a little bit just the experience so that you have like all of them in the same way. And for example, the legend is within the plot, but this is really minor stuff. Yeah. And yeah, overall, I think you got the concept and you understand what this is about, and you have compared the different types. And just one out of curiosity, in the first part when you show the results and you used already 7 beams, did you also try like less beams, kind of 5 or
5 to 9 here it is, but I choose to take 7.
Okay. Okay, no, just out of curiosity, is nothing wrong or
okay.
Yeah.
Thank you, Radana.
Thank you very much.
If I'm not mistaken, you have performed the particle therapy masterclass
Yes,
the
I
first
have.
year.
Yes,
Maybe you want to say something on your experience, and then we go to Albana to give us more details. Yeah, you want to say something from point of view of organizer?
Yes, with together with Professor Mimosa Vistova, I was part in the first year in the particle therapy master classes, and we work it I can't remember, we work it together with Albanian and Macedonian people, students here, sorry. Was very good, very nice experience. A lot of things to know and to explain for the students. Was very I can think different master class, I can say, for us. Was first year, and I was very happy to be part. And I have just a good comment from my students.
Mm-hmm. Actually, this is what I wanted also to ask you. If you have any follow-up from Novi Sad, from Serbia, we have the feedback that 50% of the students, the high school students that they did it, they enrolled at the university on this kind of classes next year. You have any such feedback from your side? If not, it would be good to try to keep some records and to find a way of to see what is the follow-up of the students, no?
Yes, I can't remember just that was the students in the 4th year in the high school, and graduated that year. And now we have 2 from the students in the physics department students. And I think that this was also one reason, I can say, to follow, for example, this degree.
Okay, thank you very much for that.
So good, so beautiful for us. Thank you very much.
Okay, Albana, so now on you, and you can give us a little bit your views from the point of view of local organizer, and then continue with the quiz that will be the end of our session.
Great. Yeah, I think I share also what Redona showed and how was her experience. Also for me, it was unfortunately virtually. I would have loved to be there in person with students or with high school pupils. We organized in 2000 and so 2021 for the first time we organized with university students because it was basically the first time to organize and then to know better about the topic. And this year we had quite a successful masterclass organizing it together with students that were last year. I see, for example, here named Muradi and Ulka is also here. And this year we organized it with high school pupils, and it was a Saturday. It was like the whole event, like in one day, and more than 150 students were all the time, like from 9 to 5, because basically this is the full day event. I can also share with you in a moment also, for example, how it is organized as an agenda. Basically, in the morning, we have theoretical lessons about particle therapy, how it was discovered and how it is used, different centers that are around the world at the moment. And also we organize the virtual visits, for example, at CNAU or GSI, or also at Alice. And then after the lunch break, we start immediately to do some hands-on sessions, what we did today, but with a simplified version, using basically the standalone Matrat, so that it's also easy for the students. You can understand being the last year of your high school and having all this pressure of organizing, having such, a lot of information for the first time, and then having to do all these exercises, and afterwards also to deliver something. And we were happy to see also a lot of volunteers to do the presentation, and also in English, because from 9 to 4 is you can organize in your home institute in your own language. But then from 4 to 5 is the common video conference. So we, in the same time, we connect with HITR and with other institutes that are organizing the same day. And there we present the results and then comment and see what is the take-home message, if there are more questions, and share the experience basically of the masterclass. And in the end, we ended with quiz that we can also do it together today. Is quite fun and simple, but the students start to be quite competitive at that moment, and they really want to be the first ones. And I can also share you quickly. So basically what I
maybe I can take the opportunity while you are bringing up the agenda to say that during these common video conferences, often the comments of Niklas or other experts, actually people that are using it for therapy in CNAU or in other places, are surprised with the treatment plans that the students come up with. Despite this packed day and having contact with this topic for first time practically. And actually they are surprised also with the creative and full of imagination plans that are really good plans. So please go ahead, Albana.
Sure. I can share one of my desktops. So I guess, yep. Probably now you see, I hope you're seeing this.
Yes, we see.
Okay. So basically this is the Indigo page of what we organized this year. And as I said, that in the beginning we have basically some theoretical parts. So here is a mixture of English and Albanian for the titles. We contacted the professors that were at universities in the different countries that we are participating, and they gave the theoretical part, like the formation, kind of the theory behind. and also different helpful videos that are available in the masterclass toolkit that is organized, and I guess Jota has talked about it. It's basically Google Drive folder with all the necessary materials that you could use. Probably in this drive you can find also material that are in your mother tongue, not only in English but also others. And afterwards, basically, is the hands-on sessions, or you have more or less, or depending how you would organize it locally, kind of 2.5 hours where you try to give different scenarios. For example, the examples that Niklas has explained, for if you organize in different days, you can have a scenario and say, okay, now let's do this plan, or you follow along different examples and see they can do the exercises together with you and also have the feedback directly. And in the end, together with maybe their teachers, if you are organizing this with high school pupils, with the help of their teachers, they organize or that they prepare the presentations. And the last part, as I explained also before, is the common video conference where, take a moment. It lasts 1 hour, and after all the presentations that are of the day, and in the last part we ended with quiz. And I guess this is basically this as an overview for sharing the experience and in short way.
Thank you, Albana. Maybe you want to start the quiz now?
Yeah, sure. So the quiz is done. Let me share again. Okay, let me also open the chat. Second window.
So you are invited all to do it if you wish.
Exactly. If you can go to kahoot.it or .com, let me also share it in the chat so that you can access it easily. Okay, sorry, that was my bad. Just give me a moment, I'll come to you very soon. Just my browser decided to. All right. And I'll, the moment that you enter, you can use your phone or with a computer. The moment if you Google just Kahoot, and then I'll give you a code where you can enter and be part of the game. And when it's open, please continue as a guest, depending on how it will be shown in your phone or in the computer. The classical mode. And I will share with you after the game is loaded. I'll share with you a code and you can enter that code so that you can access. So basically, this is the code. I can type it also on the chat for everyone. So 453 5446. And I can also expand the QR code if you want to access it directly this way. Okay, I see people joining. And while we wait, I can say, so there are around 10 questions in total, and you have the options. There are 4 options. One of them is the right answer, and you get point not only by getting the right answer, but also who is the fastest to press basically the button. This is how it's calculated. So don't be surprised when you say, yeah, I got it right, why I'm not listed within the winners. All right, so I'll give 1 more minute, so please join. And as also Jota said, so this is for fun, only if you want to, is no grades in the end. It doesn't depend, your results in here, they don't depend on the fact if you will get a certificate in the end or not. So, all right. So we are 38, and in the Zoom at the moment we are 50 people. I would say that I will start unless anyone need those last 10 seconds to enter. If not, I see the number quite stable, so I will continue. All right, so let's start. I can adjust the volume. Sometimes it's also nice when you have a little bit of music in the background. Let's start. So which physical principle is important for hadron therapy? Brad Pitt, Brad Valley, Bragg Peak, or Bill's Peak? I hope you all got this one. And yes, is Bragg Peak. And the next. Okay, Raika is leading the board. Next question, which type of interaction is dominant between proton or ion beams with electrons from molecules of human body? So electromagnetic force, weak, strong force, or gravitational force? I guess I hope yes, so it's the electromagnetic force. Moving to the next question, and of course in between we'll see the scoreboard. Now we have Dimitris leading the board. And next, from the picture below, what kind of particles create such dose distribution? So attention, look carefully. Are they protons, carbon ions, photons, or pions? We saw some pictures like this, similar pictures like this today. So I hope many of you get this right. Let's see. So this is photons, because we have quite, the radiation is basically all over the head phantom. And Adam is leading the scoreboard. Next, the fourth question. The most commonly used ions for therapy are uranium, argon, magnesium, or carbon ions. I guess this was easy. And of course, the carbon ions. And I'm impressed. Every one of you got it. And Dimitris is coming back at the first place. The fifth question, what is the unit for absorbed dose? This is Joule, Newton, gray, or green? And my father is calling. Okay, so as we see, it's gray. And seeing the scoreboard, Dimitris is keeping that first place. The sixth question, how do we call the treatment using ionizing radiation to kill cancer? Is radiodiagnostic, radiotherapy, radiostation, or radiogaga? This is an easy one, so I don't expect any errors from you all in here. And precisely, it's radiotherapy. Okay, Dimitris is on fire and the highest streak of 6. Great job. 7. Dose on the healthy organs using hadron therapy instead of X-ray therapy is bigger, smaller, I don't know, or equal. So it's dose and in the healthy organs. Be careful with the keywords. Exactly, so it's smaller. This is the point. And we go to the 8th question. Synchrotrons are used for accelerating photons, heavy particles, treatment time, or studying. I would have loved to see synchrotrons accelerating the studying process. Exactly, so heavy particles like protons or ions. And Dimitris is keeping his first place, but we have the last question. Careful. We use a CT machine for radiation delivery, reducing background radiation, shielding, or imaging. Imaging, it's the correct answer. And let's see. We have on the 3rd place, so come. Dimitris on the 2nd, oh no. And we have on the 1st place, Adam. So congratulations to the finalists and to all of you. This was basically the idea behind, we can also take for fun a screenshot. If I, great, I'll stop the sharing of my screen and
Thank you very much, Albana. And I think this is the end of the session. I don't know if we want to have a picture.
Yeah.
Of course, we
okay.
If we have 1 minute, you can switch on your camera. And may I ask to one of the students, please, to help me in taking the picture. Cameron or Joseph, can any one of you take the picture?
Yeah, why not? Thank you.
They're doing it.
Okay, great. Great. Okay.
Yep.
Done.
Okay, so I hope you enjoyed the session. We try to have a fair share on specialization and giving you details from the experts for the future experts, but also to give you an idea of the simplified particle therapy masterclass that you can perform at your own institutes, and you have also material to perform classes at higher level if you wish. As I said, we are available for any questions, and please send the results of your exercises by email to Nicholas and Manjit. So I pass it back to you, Angelica.
Thank you. Thank you very much, Jota, and all the guys for